The Big Bang is considered the birth of space, time, matter, and energy. But what if it wasn't the beginning at all? What if the Big Bang was actually the explosive exit of something else? A cosmic eruption not from nowhere, but from a place we can't see and may still be connected to. Some physicists believe the Big Bang could have been a white hole. It's a bold idea, one that links black holes, wormholes, and quantum gravity into a single, mind-bending possibility. If true, it could mean our universe was born from the death of something else. Let's explore the theories, the math, and the mysteries, and see whether the universe itself is the ultimate white hole. Beyond the Bang, rethinking the standard cosmological narrative. The story we've long been told begins with a bang. Not just any explosion, but the biggest one imaginable, the birth of everything. From a tiny, hot and dense point, the entire universe expanded outward in a flash. Time and space themselves began in that moment. This is what we call the Big Bang. Over the decades, this idea has become the foundation of modern cosmology. It appears in science books, planetarium shows, and even children's cartoons. The universe, as we understand it today, began nearly 13.8 billion years ago in that sudden burst of creation. Galaxies formed, stars were born and died, planets took shape. Life eventually appeared. This narrative feels complete and neat. The Big Bang theory has been remarkably successful. It explains why distant galaxies are moving away from us. It predicts the cosmic microwave background, or CMB, that faint afterglow of heat still seen across the sky. It even gives us a good idea of how elements like hydrogen and helium formed in the early minutes of the universe. But despite these successes, not everything fits as neatly as we thought. Take, for example, the question of what caused the bang in the first place. The standard model doesn't actually say. It begins at the moment the expansion starts. Anything before that, if there even was a before, is outside its reach. This is a boundary, a limit built into the theory itself. That bothers many scientists. A good theory should not just describe what happened. It should also explain why it happened. There are other puzzles too. When we look at the universe on a large scale, it seems to be smooth and uniform in every direction. That's strange. Regions of space that are now billions of light years apart appear to have the same temperature and density, even though there wasn't enough time for light or anything else to travel between them and even things out. This is known as the horizon problem. How did such far-off parts of the cosmos end up so similar? Then there's the flatness problem. The shape of space-time seems to be perfectly balanced, not curved inward like a sphere, not outward like a saddle, but flat. And not just close to flat, but so extremely flat that even small differences in the early universe should have grown into big ones by now. This level of precision seems unnatural, as though the universe was fine-tuned from the beginning. These problems haven't been ignored. In the 1980s, a concept called cosmic inflation was introduced by physicist Alan Guth to patch some of these holes. Inflation says that just after the Big Bang, the universe expanded faster than the speed of light for a tiny fraction of a second. This sudden stretching would smooth things out, solve the horizon problem, and make space appear flat. It was an elegant solution, but it raised new questions of its own. Where did inflation come from? What started it? And why did it stop so perfectly, allowing stars and galaxies to form? The idea of inflation itself depends on fields and particles we haven't yet observed directly. It adds more moving parts to the model and more assumptions. The Big Bang alone already began with an undefined explosion. Now we've added an invisible field to explain the explosion's aftermath. Some researchers began to wonder if we were solving mysteries with more mysteries. As telescopes have grown more powerful, the universe has become easier to observe and harder to explain. The CMB has been mapped in incredible detail. Galaxies have been catalogued by the millions. And with every new discovery, the standard story is stretched and bent to make room. Dark matter was introduced to explain why galaxies don't fly apart. Dark energy was added to explain why the expansion of the universe is speeding up. These aren't small corrections. Today, the things we can't see, dark matter and dark energy, make up about 95% of the total universe. We've built a model on the sliver we can observe. This has led some scientists to ask a bold question. What if we're missing something big? What if the standard narrative, helpful as it's been, is only one version of the truth, and maybe not the most complete one? Rethinking the universe's beginning doesn't mean throwing out the Big Bang entirely. It means looking at it with fresh eyes. Many researchers still accept that the universe expanded from a dense state, but they want to know more about what came before, or whether before even makes sense in this context. They want to test new ways of thinking, ideas that might account for the same observations, but with fewer assumptions or deeper insights. Some are turning to quantum physics, which might offer a more complete picture of the very early universe. Others are exploring models where the universe has no beginning at all, just cycles of expansion and contraction. Still others are looking at how space and time themselves could emerge from deeper structures we don't yet understand. There is a quiet revolution underway in cosmology, driven by a growing sense that our most trusted story may need updating. That's what science does. It builds on what works, questions what doesn't, and opens the door to new ways of thinking when old ones fall short. In this moment of reflection, the universe itself becomes a kind of detective story. The clues are scattered across the sky, and each one offers a glimpse of something deeper.
So, where exactly did everything start? Before we answer that question, I just want to say that I've been reading your comments, and so many of you mention that you use these videos to relax or fall asleep. But now that summer's here, with longer days and later sunsets, getting good sleep can be tricky. That extra sunlight can quietly throw off your circadian rhythm, making it harder to wind down or stay asleep. That's where Manta sleep masks come in. These aren't your average sleep masks. They feature 100% true blackout, blocking all light with zero gaps. Whether you're a side sleeper, a light sleeper, or just want deeper rest, the C-shaped eye cups make a huge difference, providing total darkness, breathability, and zero pressure on your eyes or lashes. Along with the Pro and the 100% pure silk Manta sleep mask, if you like falling asleep to music or calming sounds, check out the Manta Sound Mask. It has razor-thin Bluetooth speakers built right in, with 20 hours of battery life. Our viewers get 10% off by clicking the link in the description and using the code HORIZONS10 at checkout. Try it risk-free for 60 days, and if Manta doesn't transform your sleep, you get your money back. Big thanks to Manta Sleep for sponsoring this video. Now let's get back to the initial singularity.
In general relativity, a singularity appears when certain quantities, like density or the curvature of space-time, become infinite. Infinity in physics is a red flag. It means our equations no longer make sense. The outputs aren't just big, they're undefined. It's like dividing by zero. The math breaks down and the rules that usually guide us fall apart. That's what the initial singularity is. It's the theoretical point at the beginning of time, where the entire universe was compressed into something with zero volume, but infinite density. According to Einstein's equations, if you go back far enough, this is what you get. It's not just that things were crowded or hot, it's that space itself had no size, and time had no duration. While general relativity predicts this singularity, it also tells us that we can't actually describe what happens at that point. The very framework of the theory becomes unusable. Space-time, as described by relativity, curves so sharply that the equations no longer apply. The singularity becomes a boundary, not just in space, but in knowledge. It's a place where the known universe ends. In this sense, the singularity is more like a warning sign than a destination. When physicists see a singularity in their math, they don't usually take it to mean that something infinite is physically real. Instead, they take it to mean the theory has reached its limits. It's a sign that something else is needed, another layer of understanding that takes over where general relativity fails. The initial singularity isn't unique to the Big Bang. We see a similar idea in black holes. At the center of a black hole, general relativity also predicts a singularity, an infinitely dense point hidden beyond the event horizon. In both cases, the theory leads to a mathematical edge. There's another feature of singularities that's worth noting. They can be naked or clothed. In black holes, the singularity is hidden by the event horizon. Nothing, not even light, can escape it. That's what keeps the singularity out of view. But with the Big Bang, there's no horizon. The singularity is at the beginning of everything. It's not tucked away inside something. It's exposed, open, and in a sense, visible to the equations. This makes it even more troubling. It's not just a weird region in space. It's the very origin of space and time. Some physicists argue that this singularity is simply a placeholder, an artifact of trying to use general relativity where it doesn't belong. They believe that if we had a full theory of quantum gravity, a theory that blends quantum mechanics with gravity, we could smooth out the singularity. The point of infinite density might be replaced by something more stable, more understandable. But for now, that theory remains out of reach. It's important to understand why general relativity breaks down here. The theory is built on the idea of smooth, continuous spacetime. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. This works incredibly well for stars, galaxies, and the motion of planets. But at extremely small scales, where quantum effects dominate, this smoothness falls apart. Space and time are no longer continuous. They become uncertain, jittery, unpredictable. At the singularity, the density and energy are so high that quantum rules must come into play. Yet general relativity doesn't include them. This is why the singularity is so puzzling. It represents a clash between our best theories. On one side, relativity gives us the structure of space-time. On the other, quantum mechanics gives us the rules of matter and energy at small scales. At the singularity, both are needed, and both are incomplete. One of the more fascinating aspects of this situation is that time itself may not exist in the way we think it does near the singularity. In relativity, time is part of space-time. It stretches, compresses, and curves along with space. But at the singularity, where space-time curves infinitely, time could behave in ways we can't imagine. It may not even exist at all. If that's true, then talking about before the Big Bang might not make any sense, because before implies the existence of time. This leads to deep philosophical questions, as well as scientific ones. Is the singularity a real thing that once existed? Or is it a sign that our understanding is missing a deeper truth? Is the universe truly born from a single point? Or is that just what our current tools suggest? Many physicists believe that some future theory will replace the singularity with a more complete description. One possibility is that the universe never reached infinite density. Instead, it may have reached a state of maximum but finite density, something incredibly small and hot, but still describable. Another idea is that the singularity is not the beginning of time, but a transition, a kind of doorway between a collapsing universe and an expanding one. For now, the singularity at t equals to 0 remains a frontier. While we can't yet see beyond it, we know it holds the key to deeper insights. Cosmic inflation and its discontents. With all its successes, inflation sounds like a powerful idea, but the more scientists look into it, the more complex it becomes. It's not enough to just say the universe inflated. We have to ask, what made that happen? Inflation depends on something called the inflaton field. This is a hypothetical field, kind of like a force that fills space. During inflation, it would have had a high energy level, causing space to expand rapidly. Then, at some point, this field would have decayed into the particles and energy that make up everything we see. This idea works well on paper, but no one has ever observed this inflaton field. We don't know what it is, what it's made of, or why it existed in the first place. Even more puzzling is what started inflation. Did the inflaton field just happen to be in the right state by chance? Was it triggered by some earlier event? The theory doesn't tell us. It assumes inflation began, but doesn't explain the true cause. This leaves us with a gap in our understanding, right at the moment where answers matter most. Then there's the issue of how inflation ended. In theory, inflation stops when the inflaton field rolls down to a lower energy state. This triggers what's called reheating, where the universe becomes filled with particles and radiation. But exactly how this transition happened, how energy from the field turned into real matter, is still unclear. The details depend on the unknown properties of the inflaton itself. Inflation also comes with its own set of strange predictions. One of these is the idea of eternal inflation. In some versions of the theory, inflation never fully ends. It stops in one place, but continues in others, creating an endless chain of expanding regions. Each of these regions could become its own universe with its own laws of physics. This leads to the so-called multiverse, a collection of bubble-like universes, all separate and possibly unknowable to each other. For some scientists, this idea is exciting. It offers a way to explain why our universe has the properties it does. Maybe we just live in one bubble where the conditions are right for life. But for others, it's deeply troubling. If we can't observe or test these other universes, is the idea even scientific? Inflation theory has become so flexible that some physicists worry it can be made to fit almost any observation. If a theory can explain everything, it might end up explaining nothing. A good scientific theory makes bold predictions that can be tested and possibly proven wrong. But if inflation can be adjusted to match new data, no matter what that data is, then it becomes harder to evaluate whether the theory is actually correct. Some researchers have explored alternative models, including ideas where the universe has no beginning at all, or where it bounces from a previous contracting state into the expansion we see today. Others look at models where inflation is replaced by a more complex phase transition in the early universe. But all of these are still works in progress. None have been confirmed. Meanwhile, experiments continue. Scientists look for clues in the CMB, hoping to find patterns that inflation predicts, such as specific kinds of polarization or gravitational waves from the early universe. So far, no clear signal has confirmed the inflationary model, but the search goes on. What remains clear is that inflation is not a complete answer. It fills in gaps left by the Big Bang model, but it creates new ones in return. It's a step forward, but not the final word. We're still left wondering what came before, what caused inflation to begin, and whether the whole picture we've built is just a chapter in a deeper story we don't yet understand. The limits of general relativity at the dawn of time. General relativity is built on a set of equations known as the Einstein field equations. These equations relate the geometry of spacetime, described by a mathematical object called the metric tensor, to the energy and momentum of whatever matter is present. In simple terms, they tell us how matter shapes spacetime, and how that curved spacetime tells matter how to move. But the equations only work if the curvature is not too extreme. The geometry becomes wild and unpredictable as we push closer to the singularity. Physicists have known about these problems for a long time. In fact, in the 1960s and 70s, Roger Penrose and Stephen Hawking developed a set of theorems showing that singularities are not just strange features of particular solutions to Einstein's equations. They are unavoidable. If you take general relativity seriously, and if you assume certain basic things about matter and energy, then you are forced to conclude that the universe began with a singularity. The theory predicts it. But that's exactly why we know something has to change. The singularity theorems don't tell us what happens at the singularity. They only show us that general relativity can't go past it. To see what's on the other side of that line, we need a theory of quantum gravity. What would such a theory look like? Nobody knows for sure, but many attempts have been made to build one. One approach is called loop quantum gravity. It replaces the smooth curves of space-time with tiny loops of quantum information. In this view, space is not continuous. It's made of discrete chunks, like pixels on a screen. Time may be the same way. When you look at the universe through this lens, the singularity disappears. Instead of a point of infinite density, the universe bounces. It reaches a minimum size and then begins to expand again. Another approach is string theory. In this model, the basic building blocks of the universe are not particles, but tiny, vibrating strings. These strings can stretch and twist through higher dimensions beyond the ones we see. The added complexity of string theory may allow it to avoid the infinities that plague general relativity. Some versions of string theory include features that naturally smooth out the beginning of the universe, replacing the singularity with something more manageable, perhaps even something that connects to a previous phase of existence. Still, other ideas focus on modifying general relativity itself, adding new elements to its equations. One possibility is torsion. In standard general relativity, space-time has curvature, but not torsion. Curvature bends space, torsion twists it. By including torsion in the theory, we may be able to describe regions of extreme gravity without running into singularities. Some researchers have explored this through a framework called Einstein-Cartan theory, which allows space-time to have both curvature and torsion. In these models, the twist of space-time may act as a kind of pressure that prevents the universe from collapsing into a singularity. But so far, none of these theories have been confirmed. They remain mathematical models, possible solutions to a puzzle we don't yet fully understand. We can't test them directly because we can't observe the universe at the exact moment of its birth. The earliest light we can see comes from about 380,000 years after the Big Bang, when atoms first formed and the universe became transparent. Before that, we have only indirect clues, patterns in the CMB, the distribution of galaxies, and the laws that hold in particle physics. Even with these clues, it's hard to know what happened when the universe was only a fraction of a second old. The physics of that time is unlike anything we can study in a lab. Temperatures were trillions of degrees. Densities were beyond anything we see in stars or black holes. Space-time itself was in flux, perhaps not even behaving in a way we would recognize. This is why physicists continue to look for a better theory, one that blends the strength of Einstein's insights with the strange rules of the quantum world. Until we have that theory, we can't truly understand what the Big Bang was, or what came before it, if before even means anything. A universe from nothing, or from something strange? In recent years, a new kind of question has begun to take center stage in cosmology. It goes beyond asking what happened after the Big Bang, or even what might have caused inflation. Instead, it reaches further back into the nature of existence itself. Can a universe really come from nothing? And if not nothing, then from what? To most people, the idea of nothing is simple. It means no space, no time, no matter, no energy, just complete emptiness. But in physics, the word nothing doesn't always mean that. In the world of quantum mechanics, nothing can still have structure. It can still do things. In quantum theory, empty space is not truly empty. It is filled with what scientists call quantum fields. These fields can have fluctuations, tiny random changes that happen because of the uncertainty built into the quantum world. These fluctuations are real and have been measured. In fact, these are the same kinds of fluctuations that help explain how particles appear and disappear in high-energy environments, like near black holes or in particle accelerators. So some physicists have asked, If a quantum fluctuation can create a particle, could a large enough fluctuation create an entire universe? This idea has led to a concept called quantum cosmogenesis, the creation of the cosmos from quantum processes. One of the most well-known versions of this comes from physicist Edward Tryon, who suggested in the 1970s that the universe might be a giant quantum fluctuation. Later versions of this idea were expanded by researchers like Alexander Vilenkin, who developed mathematical models showing that a universe could spontaneously appear from a quantum vacuum. These models often rely on the idea of a closed universe. A closed universe has zero net energy. The positive energy of matter and radiation is exactly balanced by the negative energy of gravity. In such a case, the total energy of the universe is zero. That balance could, in theory, allow the universe to come into being without breaking any physical laws. Nothing becomes something, and no energy is borrowed. But this raises an important question. Where did the quantum vacuum come from? If it exists, it's not really nothing in the purest sense. It's a kind of something. It has properties. It allows for activity. So if we say the universe came from nothing and then describe a space full of quantum fields, are we really talking about nothing at all? Some physicists argue that we're stretching the definition too far. The nothing used in these models is more like a special kind of pre-universe, a place with no matter or time as we know it, but still governed by rules and structure. This has led others to wonder whether something more exotic than a quantum fluctuation might be behind the birth of our cosmos. One idea that's gained attention in recent years is the possibility that our universe came out of a white hole. White holes are the theoretical opposite of black holes. While a black hole pulls matter in and doesn't let it escape, a white hole pushes matter out and doesn't allow anything to enter. They come from the same equations that gave us black holes, but they seem much stranger. And so far, we've never seen one. Still, on paper, they are possible. Some researchers suggest that the Big Bang could have been a white hole event. In this view, what we call the beginning of our universe was really the outflow from some other region of space-time. In fact, one idea proposes that black holes in one universe could create white holes that give birth to new universes. If true, this could mean our universe didn't come from nothing, but from the interior of a black hole in another cosmos. This kind of theory ties into ideas about the multiverse and bounce cosmologies. Instead of a single universe appearing from nowhere, we might be part of a larger network of connected universes. Each one could be born from the death of another. This removes the need for a beginning in the traditional sense. It replaces it with a cycle or a branching tree. There are also ideas that suggest space and time themselves might emerge from something even deeper, something beyond space and time. Some of these theories suggest that what we see as space is actually the result of more fundamental bits of information, woven together in complex ways. If that's true, the universe might have emerged from a state where space and time didn't yet exist. Other models explore the idea of a pre-Big Bang universe, a universe that contracted before expanding again. These bounce models don't require the universe to emerge from a singular point or from nothing. Instead, they suggest our universe is just the latest phase in a much older and ongoing process. But here too, questions remain. If the universe bounced, what made it contract in the first place? What laws govern that earlier state? Could it have been infinite? Or does even a bouncing universe have some deeper origin that we have yet to understand? These models remain educated guesses, built on what we know but reaching far beyond what we can test. Still, they show how far the conversation has come. Scientists are no longer just asking what happened after the Big Bang. They're asking whether the Big Bang was really a beginning at all. Some thinkers have even proposed that trying to find a first cause may be the wrong question entirely. In quantum mechanics, cause and effect can behave in ways that don't match our everyday logic. Events can happen without a clear reason. In a similar way, the universe might simply be a self-contained system with no need for a cause or a moment of creation. This challenges our deepest instincts. Human minds are trained to look for beginnings and reasons. We expect a chain of causes to lead back to some ultimate source. But nature might not play by those rules. The universe could be like a circle with no starting point, or it could be like a story where the first page has been lost, and all we can do is read forward and guess at what came before. What exactly is a white hole? A time-reversed singularity. Black holes were once thought to be mathematical oddities, but now we know they are real. We've observed their influence on stars and even captured them in images. But there's another object predicted by the same equations, an object that is far less understood and far more mysterious. A white hole is a region where nothing can enter, but energy and matter can leave. A white hole has an event horizon, just like a black hole, but with the arrows of time flipped. For someone approaching a white hole, there's no way to go inside. The closer you get, the more you're pushed back. The laws of physics simply do not allow anything to cross that boundary in the inward direction. To understand how this idea came about, it helps to look at the math behind both objects. In the 1910s and 20s, scientists studying Einstein's equations found a solution that described a black hole. This solution is called the Schwarzschild metric. It describes the gravitational field around a point mass, a very simple and ideal case. The equations show that when too much mass is squeezed into a small enough space, an event horizon forms. And once that happens, anything that passes this horizon is pulled in toward the singularity at the center. But the Schwarzschild solution actually contains more than just a black hole. If you extend the mathematics in both directions through time, a surprising feature appears. In one direction, matter falls into the singularity. In the other, matter comes out. That second path is the white hole. The full solution includes both, a black hole in the future and a white hole in the past. The white hole appears as a kind of reverse collapse, where matter and light erupt from a single point and spread outward, but never return. In the math, this all makes sense, but in the real world, we don't see white holes. We see black holes in the centers of galaxies. We see their influence in X-ray emissions and gravitational waves. But we've never detected a white hole or anything like it. If general relativity allows for white holes, where are they? One answer is that white holes are unstable. If you take the ideal math and add even a small amount of disturbance, say some extra particles nearby or a tiny asymmetry, the white hole quickly breaks down. The equations become chaotic. The clean, ideal picture starts to fall apart. The energy pouring out of the white hole interacts with its surroundings, and the system collapses. This makes white holes nearly impossible to sustain in practice. They might exist in theory, but nature doesn't seem to use them. Another answer comes from how white holes might form, or fail to form. Black holes can be made from stars. When a large star runs out of fuel, its core collapses under gravity. If the core is massive enough, it compresses past the point of no return and becomes a black hole. But there is no known process in the universe that forms a white hole. There's no known way to gather matter, reverse time, and launch it outward from a single point. The equations of relativity allow it, but the physical world seems to choose otherwise. Still, the idea remains. White holes are a reminder that the laws of physics, at least as written in general relativity, don't prefer one direction of time over another. The equations work the same whether time flows forward or backward. From the standpoint of the math, both are equally valid. Imagine standing near a white hole, assuming one could exist. You would see matter and light streaming out from an invisible surface. The energy would come from a point in the past that can't be reached. The moment anything tries to get close, it's pushed away by the structure of space-time itself. The past singularity acts like a source that can't be approached. In this way, the white hole looks like a kind of cosmic fountain, a place where matter appears, flows out, and then is gone. Of course, such objects would violate the arrow of time as we know it. Eggs break, but don't unbreak. Stars burn fuel, but don't reignite. Entropy increases. Yet white holes suggest a world where time could flow the other way, where cause and effect might look different. The laws of physics, at their core, don't seem to forbid time reversal. They just don't seem to allow it easily in nature. In quantum theory, some models of black hole evaporation suggest that a dying black hole might eventually become something like a white hole. As the black hole shrinks and loses mass through Hawking radiation, it could reach a point where it reverses its role, turning from a sink into a source. This idea is still new and very uncertain, but it gives white holes a possible role in the real universe, at least in the far future. Mathematics that allows white holes, but nature that may not. In the 1950s and 60s, physicists like Martin Kruskal and George Sikaris found a way to extend the Schwarzschild solution of Einstein's field equations. They used a new set of coordinates that removed the apparent singularity at the event horizon. In these coordinates, the geometry became smooth. The horizon wasn't a wall, just a region where the original math had been misread. What emerged from this new way of looking at the Schwarzschild geometry was surprising. The full or maximal extension didn't just include one region of space, it included four. There was the region outside the black hole, where we live. There was the black hole interior, where space leads inward to the central singularity. Then there was a kind of reverse version, a white hole. And finally, there was a second universe, disconnected from ours except through a narrow bridge. All of this came from one mathematical solution. In the extended Schwarzschild diagram, often called a Kruskal diagram, these four regions are laid out like quadrants on a graph. Region 1 is the universe we know. Region 2 is the black hole interior. Region 3 is a second parallel universe, and Region 4 is the white hole region. This white hole is not placed in space, but in the geometry of space-time itself. It exists not next to the black hole, but before it, in the sense that objects can come out of it, but nothing can go in. Between these regions lies a connection sometimes referred to as an Einstein-Rosen bridge. It's what people often call a wormhole. The bridge links the black hole and white hole regions together. It's not a stable tunnel that one could travel through in any practical sense. It pinches off too quickly. But it's still part of the mathematical structure. It shows that under the rules of general relativity, black holes and white holes aren't separate ideas. They're tied together by geometry. All of this comes straight from the equations. You just let the math play out to its logical end. And when you do, white holes appear naturally. But many physicists believe that white holes, at least in their ideal form, can't actually exist in the real universe. One reason is that white holes seem to be extremely unstable. What if a particle, a photon, or even a single atom approaches the white hole's event horizon? In a perfect vacuum, far away from any disturbances, the white hole can survive. But introduce just one small disturbance and everything begins to break down. The delicate structure of space-time begins to fall apart. The equations no longer describe a white hole. The region quickly becomes chaotic and may collapse into a black hole or into something even more complicated. This instability makes white holes very different from black holes. A black hole is robust. Once it forms, it's hard to get rid of. Matter can fall in. Light can spiral into it. It can interact with its environment. But none of that changes the basic shape of the black hole. It might grow larger or spin faster, but the horizon stays intact. A white hole, on the other hand, is like a house of cards. One small push, and it falls apart. Some of this comes from the direction of time. A black hole has a clear origin in time. In order for a white hole to exist, it must have always been there. Its past cannot contain anything falling in. Its event horizon has to be there from the beginning. And its singularity must be in its past, not its future. In physics, entropy is a measure of disorder. It tends to increase over time. Systems evolve from ordered states to disordered ones. This is one of the few laws in physics that gives a direction to time. It tells us which way is forward. When matter falls into a black hole, the total entropy of the universe increases. But a white hole would have to take a very disordered system, perhaps a chaotic mass of particles and radiation, and eject them all in just the right way to create an ordered state outside. This would mean entropy decreases over time, which goes against everything we've seen. Some have tried to get around this by proposing that white holes might only appear under special conditions. Maybe they don't form naturally, but can arise from extreme quantum effects. Maybe they are rare events, not stable objects. Maybe they only exist in the deep past or the far future of the universe. Some models suggest that the information that enters into a black hole isn't lost inside forever. Instead, it's released at the end, through a white hole-like phase. In a purely mathematical universe, you might find white holes sitting beside black holes, forming and disappearing in symmetric ways. But our universe is not purely mathematical. It's messy. It's full of particles, fields, noise, and heat. And in this noisy, imperfect world, white holes struggle to survive. Another issue has to do with energy. In general relativity, you can track how energy moves through space-time. For a black hole, energy flows inward. For a white hole, it flows outward. But this creates problems when you try to match the white hole to the surrounding universe. Where does the energy come from? What keeps it flowing? If the white hole is just appearing suddenly, blasting out matter and light, what's powering it? The theory doesn't provide a clear answer. In fact, any white hole in our universe would violate the basic idea of conservation of energy, unless it's somehow connected to another region. This leads some theorists to suggest that white holes are not isolated objects, but parts of a larger system. They might be entrances to wormholes, or they might be matched to black holes in some kind of balance. In this picture, a black hole pulls in matter from one universe, and a white hole ejects it into another. The total energy is conserved across both regions. But again, there's no evidence that this happens in nature. It's an idea that works on paper, but not one we can test. At least, not yet. Entropy in reverse, the thermodynamic dilemma of white holes. In physics, there are laws that seem to be written into the bones of the universe. Some can bend, others break under extreme conditions. But one law stands apart for its stubborn consistency, the second law of thermodynamics. It says that the entropy of a closed system, the amount of disorder or the number of ways a system can be arranged, tends to increase over time. It's a rule not just about heat or energy, but about the very direction of time. If you want to know which way time is flowing, look at entropy. It's the arrow that points from past to future. Now imagine a white hole, a region of space that pours out matter and energy, like a movie played in reverse. It's not absorbing anything, it's releasing everything. And if that matter is structured, say not just a spray of particles but a working machine, a pattern, or even a star, then the white hole isn't just pushing out energy, it's reducing disorder, it's creating order from chaos. That's the problem. It goes against the grain of entropy. In the 1970s, Stephen Hawking and Jacob Bekenstein showed that black holes have their own entropy. They showed that a black hole's surface area, specifically the area of its event horizon, acts like entropy. The more matter or energy the black hole swallows, the larger that area becomes. And with it, the entropy of the universe grows. This was a key moment in physics. It tied gravity to thermodynamics. It suggested that even the fabric of space and time obeys the second law. But then, what about white holes? Some physicists have tried to explain this by saying a white hole would have to eject completely random, high-entropy material, just a blast of thermal radiation, like steam escaping a pot. That way, entropy wouldn't decrease. But even then, it's tricky. How did that energy get into the white hole in the first place? If the white hole has no past input, if it doesn't allow anything to fall in, then where is the entropy coming from? You can't just have entropy appear out of nowhere. That would violate the principle of conservation. This is where the math starts to feel disconnected from reality. On paper, general relativity doesn't care about entropy. It's a geometric theory. It tells us how space curves and how objects move. It doesn't include probabilities or temperature or the likelihood of one state turning into another. That's what thermodynamics and statistical mechanics do. They track the odds. They tell us what's probable and what's not. So even if a white hole makes sense in Einstein's equations, it still needs to pass the thermodynamic test. And that's where it runs into trouble. One way to imagine this is to think about a glass falling off a table. When it hits the ground and shatters, entropy increases. The broken glass has more possible configurations than the unbroken one. We don't expect the reverse to happen. We don't see shards of glass jumping up, rearranging themselves, and becoming whole again. Not because the laws of motion forbid it, they don't, but because it's vastly improbable. It would mean a massive decrease in entropy, and that goes against the second law. A white hole, in this analogy, is like a reversed movie of the glass reassembling. It's not impossible in the strictest sense, but it's not something you'd ever expect to see. The odds are overwhelmingly against it. And yet, for a white hole to appear in nature, something like this would have to happen. The disorder of the surrounding universe would have to shrink, not grow. That's why white holes raise eyebrows, not just in relativity, but in thermodynamics. There's another layer to the problem. When black holes emit Hawking radiation, they lose mass slowly over time. This process is random and it increases entropy. The radiation is thermal. It carries no information about what fell into the black hole in the first place. Or at least, that's what we used to think. More recent theories suggest that information might not be lost after all. Maybe it's encoded in the radiation somehow. But even if that's true, the total entropy still grows. The process remains consistent with the second law. If a white hole is the reverse, then Hawking radiation would run backward too. Instead of random disordered heat being emitted, the white hole would have to send out precise, structured radiation. Radiation that assembles into meaningful objects. That's not just unlikely, it's thermodynamically backward. Time symmetry is a feature of many physical laws. If you run the equations of motion in reverse, they still work. But time symmetry is broken in the real world by entropy. The universe has a built-in arrow of time because entropy increases. That's why smoke rises and spreads, but never contracts and returns to the flame. A white hole, by its very nature, challenges this. Perhaps the way to get around this is by placing the white hole outside of normal time. Maybe it exists in a bubble, a special patch of space where different rules apply. But this is a speculative idea that doesn't solve the core issue. How can a region of space eject matter in an organized way, without prior input? Even in quantum mechanics, where strange things happen all the time, entropy still grows. Particles can tunnel through barriers. States can be in superposition. But when you look at the overall behavior of large systems, the second law holds. Some physicists suggest that white holes could be real only in the quantum regime. That maybe, deep in the Planck scale foam of space-time, the normal rules break down just enough to allow a white hole to form briefly. But it would be tiny, unstable, and short-lived. Nothing like the massive, elegant structure imagined in classical relativity. In that case, the white hole becomes more of a quantum hiccup than a true object. So we are left with a puzzle. The math permits white holes, the equations welcome them, but the universe does not. At least not under the reign of entropy. If a white hole exists, it must find a way to escape the second law. or it must exist in a realm where the law no longer applies. Can a white hole form without a preceding black hole? In the traditional view, white holes only appear as one half of a complete black hole-white hole pair. When you extend the Schwarzschild geometry fully, without adding time, rotation, or anything else, you get a white hole region on one side and a black hole region on the other. Some scientists thought of this structure as a bridge between two universes. Matter might fall into a black hole in one universe and exit through a white hole in another. In that sense, the white hole's existence would depend on the black hole. It would not be independent. It would just be the reverse side of a single hole. But this setup has problems. For one, it assumes the black hole has existed forever. In real life, that is not the case. Black holes form when stars collapse, a process that takes time. There's a before and after. If a white hole is the opposite of a black hole, then we would expect it to form in the opposite way, from nothing into something, instead of something into nothing. But no one has ever seen that happen. The white hole in the Schwarzschild solution is not born. This has led some physicists to wonder whether a white hole could form on its own, without a black hole to create it or sustain it. Could a white hole just pop into existence, fully formed? Could there be a physical process that causes a white hole to appear? Some researchers have proposed that white holes could be quantum objects that form from vacuum fluctuations, like particles briefly appearing out of empty space. These white holes would perhaps be smaller than an atom and would exist for only a moment, but in theory they could exist, and if they did, they would represent a completely new kind of object, something not built from matter, but from the rules of space-time itself. In classical relativity, space-time is smooth, but quantum mechanics suggests that at very small scales, near the Planck length, this smoothness breaks down. Space and time may be fuzzy, fluctuating and uncertain. In that strange regime, the formation of a white hole might not need a black hole at all. It could emerge from the fabric of space like a bubble rising in water, driven by random energy shifts. Some of this thinking comes from analogies with black holes. In Hawking's famous theory, black holes slowly evaporate through quantum effects. As they shrink, their temperature increases. Some researchers have asked what happens at the very end of that evaporation. Does the black hole disappear completely? Or could it bounce, like a compressed spring, and become something new? In this picture, the black hole reaches a point of maximum density, then rebounds as a white hole. It would be a quantum process where space-time itself changes character. The result would be a white hole that forms not before the black hole, but after it. The black hole's end would be the white hole's beginning. This bounce model depends on a theory of quantum gravity, which we don't yet have. If such a theory exists, it could allow white holes to emerge from the death of black holes, not as part of the same eternal geometry, but as real-time transitions. The black hole collapses, reaches a limit, then explodes outward in a white hole phase. It's like a rebirth, not a reversal. If white holes can form on their own, could we detect one? A white hole would eject matter and radiation. But without knowing where or when it would appear, we wouldn't know where to look. Some have suggested that brief bursts of energy, like certain kinds of gamma-ray bursts, could be signatures of tiny white holes evaporating in space. But no such detection has been confirmed. Others have proposed that primordial white holes might still exist, left over from the earliest moments of the universe. These would be small, stable objects, nearly impossible to detect. If they exist, they might even make up part of the dark matter that fills the cosmos. But again, no evidence has been found. In all these ideas, the theme is the same. White holes could exist without black holes, but only if our understanding of space-time is incomplete. Classical general relativity offers no pathway to create a white hole from nothing. But the moment we introduce quantum rules, the door opens just a little. Suddenly, objects that were once impossible become barely possible. Not common, not likely, but maybe. Wormholes, Einstein-Rosen bridges, and the white hole exit. In the early developments of general relativity, the idea of wormholes appeared almost by accident. They weren't introduced with the purpose of explaining time travel or galactic shortcuts. They emerged from the math. When Karl Schwarzschild found the first exact solution to Einstein's field equations, it described a black hole. But decades later, in 1935, Einstein and Nathan Rosen revisited this solution and extended it. Their work led to what we now call the Einstein-Rosen bridge. At one end was a black hole, at the other a white hole. The Einstein-Rosen bridge was built from pure mathematics. It showed that if you extended the Schwarzschild geometry to its fullest, you got two asymptotically flat regions, two far apart areas of space that were linked through a throat. This full extension formed a bridge. Matter could fall into the black hole side, and, at least in the diagram, it seemed like it could emerge from the white hole side. But there was a problem. This tunnel was not traversable. That means nothing could actually travel through it, not even light. The geometry of the Schwarzschild solution pinches off too quickly. If you try to enter, the passage collapses before you can get through. In technical terms, the wormhole is unstable. It closes faster than anything can move across it. That makes it useless for travel. It's a mathematical connection, not a practical one. Still, the connection between wormholes and white holes didn't go away. If the exit of a wormhole looks like a white hole, then any discussion about wormholes must also ask, what is a white hole doing at the far end? If we ever did find a stable wormhole, or figure out how one might be created, it would need an exit. That exit, by the equations of general relativity, would have all the properties of a white hole. It would eject matter. It would repel objects. Nothing could enter from the outside, but things could come out. This picture of a wormhole with a white hole exit raises all kinds of questions. First, how would such a wormhole form? In the Schwarzschild case, the bridge is eternal. It has no beginning or end in time. It exists as a complete structure. But our universe isn't eternal in that way. Things happen. Time moves forward. So if a wormhole exists in the real universe, it must come from something. That means some process must create it and stabilize it. The stabilization part is key. In the classical equations, wormholes collapse too quickly. To hold one open, you need something exotic, matter with negative energy or negative pressure. This isn't the kind of matter we deal with in everyday life, but in the quantum world, such strange things are at least possible. The Casimir effect, for instance, shows that quantum fields can produce negative energy in certain conditions. Theoretically, if enough of this exotic matter could be gathered in the right shape, it might keep a wormhole open. In that case, the exit of the wormhole, the part that pushes matter out, would act like a white hole. It wouldn't be formed from the collapse of a black hole. It would be built directly, maybe even engineered. This leads to potential scenarios where an advanced civilization could create a stable wormhole, with the white hole end placed in a distant region. Travel through the tunnel would allow instant communication, or even movement, across vast distances. In a traversable wormhole, time flows from one end to the other. The white hole end isn't just ejecting matter, it's the destination. That has consequences for how causality works. If one could travel into a wormhole and emerge from a white hole, it might allow time travel. That's because the ends of the wormhole could exist at different points in time. You could leave today and arrive yesterday. This possibility has made physicists nervous. Time travel opens the door to paradoxes. If wormholes and white holes allow information to travel backward in time, then the logic of cause and effect starts to fall apart. That's one reason many scientists think nature must prevent such objects from forming. Stephen Hawking proposed a chronology protection principle, which says the laws of physics must prevent time machines from existing. If that's true, then stable wormholes and their white hole exits may be banned by deeper laws we don't yet know. Still, the math allows them, and the connection between wormholes and white holes runs deep. Even in more complex models, like those involving rotating black holes or charged black holes, the wormhole structures still show up in the extended solutions. The white hole region remains. It's always there, waiting at the far end of the bridge. In some models, these bridges are not between two regions of the same universe, but between different universes. The idea is that our universe might be just one part of a larger multiverse, with wormholes connecting different patches of space and time. Information or matter falling into one side could emerge in a completely different reality. Some researchers have tried to find indirect signs of white hole behavior in the sky. Fast radio bursts, for instance, brief flashes of energy coming from deep space, have mysterious origins. Some models suggest that they might be caused by tiny white holes ejecting energy. If that were true, we could be seeing the exit mouth of a wormhole. But so far, there's no proof. Other ideas are even more radical. In certain loop quantum gravity models, black holes transition. At the end of their life, they explode outward into a white hole region. That white hole might be the birth of a new universe, or it might link back to our own universe through a quantum bridge. In that case, the black hole and white hole form a complete loop, a path through time and space that includes a bounce. The connection between wormholes and white holes is strong in theory, but uncertain in practice. Still, it gives us a window into how the universe might be built, not just from matter and energy, but from connections between distant places and perhaps distant times. White holes as gateways from other universes? Our own universe could be the expanding interior of a white hole, connected by a wormhole to a collapsing black hole in a parent universe. That black hole, somewhere in an older cosmos, might have swallowed stars, gas, and light. Then, after passing through the deep interior, the matter emerged into a new region, our Big Bang. From that perspective, the white hole at the beginning of our universe wasn't just ejecting matter randomly, it was passing along the remnants of an earlier universe. This helps address a major puzzle. Where did everything in our universe come from? How could something come from nothing? This model offers one possibility. If the Big Bang is a white hole explosion, then it is not a beginning, but a continuation. What we see as the start of our time could be just a phase in a larger cycle. In the multiverse, each universe could have its own laws of physics, its own dimensions, its own birth and death. Some of them may give rise to black holes that collapse and then produce new universes through white holes. These child universes might grow, develop their own galaxies, and then produce black holes of their own. The cycle repeats, over and over. If white holes serve as the gateway from one universe to the next, then they are the mechanism by which universes reproduce. In some versions of this idea, the physical constants, like the speed of light, the strength of gravity, or the masses of particles, can vary from one universe to another. So each time a new universe is born through a white hole, it may come with slightly different settings. Over time, this could lead to a kind of cosmic natural selection, where universes that produce more black holes end up having more children. The result would be a multiverse shaped by evolutionary pressure. What would that mean for us? If our universe came from a white hole in a parent universe, then there might be a long chain of universes stretching back before ours, each one giving rise to the next, each one containing its own matter, its own space, its own history, but none of them necessarily aware of the others. The wormhole connection between them might close quickly. Once the white hole explodes, the tunnel disappears. The new universe becomes causally disconnected, no signal can return. Still, the birth event leaves a mark. The conditions of our universe, the uniformity of the CMB, the fine-tuning of physical constants, the initial burst of expansion, might all reflect what happened during that initial period. If future observations detect certain features, such as particular patterns in the CMB or unusual distributions of energy, they could hint at a past that predates our Big Bang. These clues could point not just to earlier moments, but to earlier universes. If every white hole gives rise to a new universe, and if this process has been going on forever, then there could be an endless network of universes, each with its own reality. Some of them might look nothing like ours. Others might resemble it closely. In some, life might emerge. In others, it might be impossible. This raises old philosophical questions in a new setting. Are we just one branch of an infinite tree? Is there something special about our universe, or are we just one of countless outcomes in a cosmic lottery? These are not questions with easy answers, but they show how the physics of white holes, when combined with ideas from quantum theory and cosmology, can touch on some of the deepest mysteries. They also blur the line between physics and metaphysics. If we can't see these other universes, can we say they exist? If the white hole tunnel is gone, can we ever prove what came before? Some physicists argue that even without direct evidence, the models have value. They help make sense of our universe's structure. They offer explanations for things that otherwise seem arbitrary. They provide new ways to think about space, time, and origin. Others are more cautious. They remind us that speculation without testable predictions is not science in the strictest sense. Without evidence, these ideas remain possibilities, not truths. Still, the picture is compelling. A black hole in one universe collapsing under gravity. A bounce inside, driven by quantum effects. A white hole in the next universe exploding outward. A new cosmos, expanding and cooling, filled with stars and galaxies. And somewhere within it, intelligent beings wondering where it all began. In this view, white holes are not just theoretical opposites of black holes. They are events. They are transitions. They are the birthplaces of entire realities. Whether that's true or not, the idea captures something profound. It reminds us that the universe we see may not be all there is. It may be one link in a much larger chain, each part hidden from the others, connected only through the deepest structures of space-time. Do wormholes always require exotic matter, or just exotic ideas? When physicists first began to study wormholes, they quickly ran into a problem. The geometry made sense in the math, but the energy requirements did not. The equations seemed to demand a type of matter with negative energy density. In normal physics, energy is always positive. Mass is positive, light carries positive energy, pressure is usually positive. Even in the vacuum of space, the energy levels, though small, are not negative. But the Einstein field equations don't just rely on energy being there, they care about how it's distributed. The particular arrangements of energy and pressure needed to stabilize a wormhole turn out to require a violation of what's called the null energy condition. This condition, which holds for all known types of matter and radiation, says that light rays should always converge when passing through energy. But in a wormhole, they diverge. The wormhole mouth pushes them apart. This means that whatever is inside must have a kind of repulsive gravity. It must bend space in the opposite way. This is where exotic matter comes in. Exotic matter, in this context, doesn't mean anything magical. It just means material or fields that violate the usual energy rules. It would need to have negative energy density, at least in some reference frame. In theory, quantum physics does allow this kind of behavior. In small doses, certain quantum fields can produce negative energy in very specific setups. But these effects are tiny and short-lived. They're not the kind of thing that can be scaled up to cosmic proportions. To make a stable, human-sized wormhole, using known physics, would require more exotic matter than the universe seems to contain. This has led many physicists to assume that traversable wormholes are not physically realistic. They may be mathematically consistent, but they don't align with how actual energy behaves in our universe. Yet not everyone agrees. Some researchers have started asking whether these assumptions are too strict. They wonder if the need for exotic matter comes not from the physics itself, but from the way we describe it. The Einstein equations are sensitive to how space-time is sliced and stitched together. The way you choose coordinates, how you define space and time, can affect how the energy conditions appear. In certain coordinates, a solution may seem to require negative energy, but in another, more cleverly chosen system, the same solution might avoid that need. It's a subtle point, because physics should not depend on coordinates. But energy conditions, especially when applied locally, are not always as absolute as they seem. This opens the door to a different kind of thinking. Instead of trying to generate exotic matter to satisfy the geometry, some theorists are exploring ways to reframe the geometry so it fits within allowed energy bounds. In one approach, the wormhole isn't static, it's dynamic. It opens briefly, then closes. During this brief moment, quantum fluctuations might naturally allow a tiny violation of the energy condition. Not enough to be dangerous or paradoxical, but enough to let information, or even a small object, pass through. These quantum wormholes wouldn't be stable bridges like one imagines. They'd be more like brief connections between regions, allowed only in very specific conditions. Another idea looks at higher dimensional theories. In some models of physics, such as string theory or brane cosmology, our universe is a three-dimensional slice within a larger, higher dimensional space. In these frameworks, the apparent need for exotic matter in our universe might be a shadow of something more normal, happening in a higher dimension. The wormhole could be stabilized by normal energy in the bulk space, even if it looks exotic from our limited view. Then there's the approach through modified gravity. Some alternative theories like Einstein-Cartan theory or FR gravity include additional terms that change how energy interacts with curvature. In these modified models, the energy conditions may not hold in the same way. That could allow wormholes to exist with less, or even no, exotic matter. The physics changes, so the constraints do too. One especially interesting line of research involves so-called semi-classical wormholes. In these setups, space-time is treated classically, but quantum fields are allowed to propagate through it. When the back reaction of the quantum fields on the geometry is taken into account, strange things happen. The energy-momentum tensor, the source term in Einstein's equations, can include negative components. These are not artifacts or errors. They come directly from quantum field theory. The result is that, under certain controlled conditions, quantum effects might naturally support a wormhole structure without needing invented materials. But all these approaches share a common theme. They try to work around the energy problem, not by introducing miracle substances, but by re-examining the foundations. They ask whether the need for exotic matter is a real physical requirement, or just an artifact of the way we're using our theories. Maybe the rules of general relativity, while powerful, don't capture the full behavior of space-time when quantum effects are involved. Maybe there are loopholes, not in the logic, but in the framework. Even so, these solutions remain speculative. None of them have been verified in the lab. The evidence for negative energy on large scales is still missing. And until that changes, traversable wormholes, and by extension, white holes that serve as their exit mouths, remain theoretical. The idea that wormholes require exotic matter may turn out to be too strong. They may require exotic thinking instead. A willingness to look beyond standard models, to question familiar assumptions, and to explore how the frontier between general relativity and quantum mechanics might offer new possibilities. The math of wormholes is rich. The physics is still uncertain. But the ideas continue to push us toward a deeper understanding of what space and time truly are, and what might be possible, given the right conditions. Sources of negative energy density, Casimir physics, and quantum inequalities. The Casimir effect is the most well-known source of negative energy in a laboratory. It appears when two metal plates are placed very close together in a vacuum, just a few nanometers apart. In that setup, some of the normal quantum fluctuations of the electromagnetic field are suppressed between the plates, because only waves of certain wavelengths can fit in the gap. Outside the plates, all fluctuations are still allowed. The result is a pressure difference, more energy outside than inside. This creates a tiny attractive force, as if the vacuum between the plates has lower energy than the surrounding space. In quantum terms, the space between the plates has a negative energy density relative to the vacuum. It's not that energy is missing in the absolute sense, but that this small region behaves as if it has less energy than zero. This effect has been measured repeatedly in the lab with exquisite sensitivity. And while the force is tiny, only detectable at microscopic scales, it shows that negative energy is real, and physical setups can create it. The question then becomes, can this kind of effect be scaled up or used in more extreme situations? On its own, the Casimir effect is far too weak to stabilize something as violent as a white hole. But it points to a principle that energy conditions, which we assume always hold in classical physics, can be violated in quantum theory. That includes the so-called weak energy condition, which says energy density must always be positive for any observer. Quantum fields can, at least temporarily, break that rule. There are other known sources of negative energy, though they're not easily harnessed. In quantum optics, light can be placed in a squeeze state. This means the uncertainty in one property, such as electric field amplitude, is reduced below the normal vacuum level, at the cost of increasing uncertainty in another. The total uncertainty still obeys quantum rules, but it's redistributed. In such squeeze states, some regions of space can exhibit negative energy density for brief periods. Experiments with squeezed light are already being used to improve the sensitivity of gravitational wave detectors. By squeezing the light used to make measurements, researchers can reduce the noise in one variable and improve the detector's precision. These same techniques, in theory, produce measurable patches of negative energy density inside the laser cavities. While small and fleeting, these effects open the door to thinking about more ambitious uses. If negative energy could be concentrated or maintained in a region, it might help shape space-time itself. In speculative proposals for things like warp drives, negative energy is often required to stabilize the geometry, creating a bubble of space that can move faster than light without violating relativity. These scenarios remain far from experimental verification, but they all rely on the idea that quantum effects can bend energy rules. Quantum inequalities developed by physicists like Larry Ford and Thomas Roman place some limits on how much negative energy can exist, and for how long. These inequalities act like guardrails in quantum field theory. They say that while negative energy is allowed, it must be balanced. You can have it, but not too much and not for too long. If a field dips into negative energy at one point, it must produce a positive energy pulse elsewhere or soon after. This keeps the total energy within bounds and prevents runaway violations of the laws of thermodynamics. These constraints are part of the reason why turning lab-scale negative energy into something cosmically useful is so hard. Any attempt to stabilize a white hole using negative energy would have to overcome both the weakness of the known effects and the tight restrictions imposed by these inequalities. But again, the fact that the rules allow negative energy at all, within certain boundaries, is a hint that the impossible might not be entirely off limits. One proposal, purely theoretical, suggests that if a white hole formed as the result of a quantum bounce, then negative energy might naturally arise near the bounce point. In this view, quantum geometry itself could create a kind of repulsive pressure, similar to what negative energy does. This wouldn't require building exotic setups. The energy conditions would be broken by the quantum structure of space-time itself. In other models, quantum fields living near the event horizon of a white hole might produce transient negative energy pockets, similar to the Hawking radiation process near black holes. These fluctuations could, in principle, help balance out the huge positive energy expelled by the white hole and provide a stabilizing feedback. Again, the effects would be small, but perhaps enough to extend the lifetime of the structure for a meaningful amount of time. There is no solid consensus about whether these effects could work at the scale needed. The numbers involved are extreme. The energy density of the Casimir effect, for example, is many orders of magnitude below what would be required to offset the forces near a Planck-scale white hole. But physics often starts with small examples. Quantum tunneling was once a curiosity in atomic physics, then became the basis for scanning microscopes and flash memory. Lasers, once a theoretical novelty, now light up everything from supermarket checkouts to surgical rooms. Sometimes the path from a strange quantum principle to a practical application is longer than anyone expects, but not impossible. New laboratory methods may allow for better measurements or new configurations. Advances in quantum optics, superconducting circuits, or even materials science might unlock better ways to generate and study these effects. And at the same time, progress in quantum gravity and high-energy cosmology may show where these tiny features of quantum fields fit into the largest structures imaginable: white holes, early universe dynamics, and perhaps even the cycle of universes themselves. Baby universes and the cosmological budding theory. There's a theory in modern cosmology that suggests our universe might not be a closed, self-contained bubble, but something more like a tree, one that buds, splits, and sends off shoots. These shoots aren't galaxies or star clusters, they're entire universes, tiny, self-contained pockets of space-time that split off from ours through a process known as quantum tunneling. Physicists call them baby universes. Unlike the ideas that revolve around black holes rebounding into new universes, this model suggests a different mechanism. These baby universes aren't born from the extreme collapse of matter. Instead, they bubble out gently, quietly, and almost invisibly from the fabric of space-time itself. They might even emerge not with a bang, but through a kind of escape, a quantum process that lets them tunnel out from our universe, much like particles can sometimes tunnel through barriers in quantum mechanics. This process is inspired by the same rules that govern the subatomic world. In that world, particles don't behave like solid, predictable objects. They flicker in and out of possibility. They tunnel through walls. They appear in places they shouldn't, simply because the math allows it. That same math can be scaled up, in theory, to entire patches of space-time. If a region of our universe exists in a kind of false vacuum, it could suddenly decay, and when it does, a tiny bubble of true vacuum might form. That bubble could, in effect, be its own universe. At the heart of this idea is the notion that our universe's vacuum might not be the most stable one possible. A vacuum, in physics, is a state with the lowest possible energy, or at least what appears to be the lowest. But some vacuums are false vacuums. They seem stable, but in fact sit atop a kind of energy plateau. Eventually, through quantum fluctuations, a region of space might tunnel down to a lower energy state. That change can't be localized. It creates a whole new region with its own vacuum. If that bubble detaches completely, it becomes a new universe. This budding process could produce a baby universe that's disconnected from ours, its own sealed-off space-time. From inside, the baby universe experiences its own time, its own expansion, its own evolution. From our side, the process may leave only a faint imprint or none at all. Because of how general relativity describes space-time, a bubble universe that buds off in this way might be hidden behind what's called a causal boundary. That means nothing that happens in that new universe can ever influence our own again. Some theories describe the process with help from the idea of a white hole. If a baby universe tunnels out of our own, the narrow region where it pinches off, like the neck of an hourglass, can resemble a white hole mouth. Matter and energy appear to emerge from a single point, expanding outward into a new domain. But unlike classical white holes, which are symmetrical partners of black holes, this type is one way. Nothing falls in. Everything flows outward. It's a kind of quantum birth canal, rather than a reverse death. General relativity provides the backdrop, quantum mechanics provides the fluctuations, and quantum field theory suggests the possibility of vacuum instability. Together, they paint a picture of a universe that is not static, but creative. A universe that doesn't just evolve forward in time, but also occasionally branches off sideways, spawning entirely new realms of existence. This budding might not be rare. Some inflationary models, especially the idea of eternal inflation, suggest that once inflation starts, it never really stops. Pockets of space keep inflating forever, while others drop out of inflation and become new universes. Each one forms from a bubble, separated by inflating space. If a bubble pinches off completely, nothing from inside it can reach us. It's like a soap bubble breaking away from a film. It floats off on its own, never to return. Even if the process happens close by, the geometry of space-time ensures that we won't see what's inside. What we might see, if anything, is a kind of gravitational hiccup, a burst of energy, a distortion of space, something that hints that a new universe has just blinked into being. Some physicists have tried to explore this possibility through the lens of black holes. Perhaps what we think of as the inside of a black hole is a quantum transition point. On the other side, a baby universe might form. This merges two ideas. One, that black holes are cradles for new universes. The other, that universes can pinch off through tunneling. The connecting feature is the idea of a narrow throat, a high curvature region where the rules of classical physics give way to quantum geometry. One important challenge is energy conservation. If a new universe appears, where does its energy come from? Some models suggest that the net energy of the universe might be zero. If this is true, then creating a universe doesn't require any net input. A universe can appear from nothing, so long as the accounting balances. There's also the question of scale. Baby universes would likely start out very small, perhaps at the Planck length, around 10 to the power of negative 35 meters across. That's far smaller than anything we can see or probe. But inflation could rapidly expand the bubble, stretching it into a large, flat universe, much like our own. In that way, the vastness of our cosmos might have emerged from a region once smaller than an atom. If baby universes follow the same path, they could grow to become full-sized realities. Different versions of the theory imagine different paths. Some baby universes remain attached to the parent, like branches on a tree. Others break off completely. Some form from vacuum decay. Others might emerge through fluctuations in quantum gravity. All of them are guided by the same basic principle, that space-time isn't fixed, and that under the right conditions, it can reorganize itself into something entirely new. If baby universes can form, then so could their parents. Each one gives birth to others, and the cycle continues. It's a kind of cosmic reproduction, not through biology, but through geometry and probability. Our universe, vast as it seems, might be just one leaf on an infinite tree. The Einstein-Cartan Shamar-Kibble theory and a torsion-based genesis. There is a branch of physics that asks what happens when the very fabric of space and time not only bends, but also twists. This idea comes from a lesser-known extension of general relativity called the Einstein-Cartan Shamar-Kibble theory. At first glance, it looks almost identical to Einstein's original model. It keeps the familiar concept that mass and energy tell space-time how to curve, but it adds one more ingredient: spin. Spin is a property that every fundamental particle carries. It's not spin in the everyday sense, not like a top or a planet rotating. It's more like an internal twist built into the very identity of particles. While general relativity treats mass as the thing that shapes gravity, it does not account for spin. The Einstein-Cartan-Siyama-Kibble theory steps in to correct this by saying that if particles have spin, space-time should respond to it. In this theory, the connection that describes how things move in curved space, called the affine connection, is allowed to have something called torsion. This torsion measures how much space-time twists, not just how it bends. It's a subtle change, but it leads to a powerful idea. When you combine torsion with spin, you get a new kind of gravity, one that behaves differently in extreme situations, especially at very small scales and high densities, like those that might have existed at the birth of the universe. What makes torsion interesting is that it doesn't usually show up in ordinary situations. In the low-energy world of stars, planets, and galaxies, torsion is practically invisible. But at incredibly high densities, where the spin of particles becomes concentrated, torsion kicks in. And when it does, it changes everything about how matter collapses, or fails to collapse. In general relativity, the collapse of matter under gravity can lead to singularities, but in the Einstein-Cartan theory, torsion resists that collapse. When matter gets extremely dense, the spin of particles interacts with the twisting of space-time in a way that produces a repulsive force. This repulsion doesn't show up until densities reach enormous values, but when they do, they can stop the collapse before a singularity forms. Instead of everything falling into a point, the universe, or any highly dense object, rebounds. It bounces. The collapse slows, stops, and then reverses. This creates a picture of the universe where the Big Bang was a transition from a previous phase. A prior universe might have collapsed under its own gravity until torsion effects took over, halting the fall and driving a new expansion. What follows is a big bounce, rather than a Big Bang. This bounce scenario opens the door to something that behaves very much like a white hole. Matter doesn't come from a singularity, but from an extreme but finite compression, which then explodes outward due to torsion-generated repulsion. There's no need for a wormhole, no tunnel from another region of space-time. The outward motion looks the same, an expanding region ejecting matter and radiation in all directions, but it arises from the interior physics of spin and torsion, not from an external connection to a black hole. One striking feature of this theory is that it naturally avoids many of the infinities that plague standard cosmological models. In general relativity, density, temperature, and curvature can all blow up to infinity. But with torsion, those quantities stay finite. The bounce happens at a maximum but limited density, where quantum effects tied to spin push back against gravity. Could the universe contract, bounce, and expand again, repeating this process forever? Torsion makes such cycles physically possible. It means the universe doesn't have to begin at a singularity. It can emerge from a prior stage, and possibly do so repeatedly. This model fits within the broader idea that space-time geometry can be more complicated than we usually imagine. In ordinary general relativity, space-time is described by curvature alone, how it bends. But if we include torsion, we discover a second kind of geometric structure, and in doing so, we discover that the universe may have more ways to evolve than previously thought. In the early moments of the cosmos, when temperatures were unimaginably high and particles were crammed tightly together, spin could not be ignored. The very structure of space may have twisted under the influence of this spin. That twist could act like a spring, storing up energy and then releasing it as the bounce. The expansion that followed would still be fast and hot, very much like what we observe in the real universe. But its origin would be smooth, not violent. It would not come from nothing. It would come from a prior phase that compressed into a critical state and then released outward. Some versions of the theory suggest this torsion-based bounce could also generate a kind of inflation-like expansion, without needing to invoke a separate inflation field. The repulsive force from torsion could drive an early phase of rapid expansion, spreading matter out and smoothing the universe. If so, it could help explain the large-scale uniformity of the cosmos without adding extra fields or particles. It also has implications for black holes. If torsion can halt the collapse of matter, then perhaps singularities never form inside black holes either. Instead of ending in an infinitely dense point, the matter inside could rebound in its own pocket of space. In that case, a black hole would be a transitional region, a place where matter collapses and then expands again into another space, another time, another universe. This transition would happen within a bubble of torsion-stabilized geometry. It's a kind of white hole-like behavior, not because matter escapes back into our space, but because it rebounds into another, disconnected one. In this view, torsion becomes a kind of cosmic safeguard. It steps in when things get too dense. It prevents the math from breaking. It gives the universe a way to cycle, to renew, and to continue. It's a quiet force, invisible in everyday life, but powerful enough to shape the beginning and end of space-time. While still speculative, the Einstein-Cartan-Siyama-Kibble theory has mathematical consistency on its side. It doesn't throw out general relativity, it expands on it. It adds something that was left out, something hinted at by quantum physics, the spin of matter. That spin might affect the universe as a whole, and if so, then the origin of our universe might have been a turn in the structure of space-time itself. Shockwave cosmology, Smoller and Temple's explosive alternative. In the wide landscape of ideas about how the universe began, one of the more unusual and striking proposals comes from mathematicians Joel Smoller and Blake Temple. Their work doesn't focus on quantum fields or string theory. It doesn't require hidden dimensions, exotic matter, or even torsion in space-time. Instead, their model uses the most basic building blocks of general relativity and fluid dynamics. It treats the early universe not as a smooth, continuous expansion from a singularity, but as a sudden, sharp shockwave, something more like a cosmic explosion spreading through a pre-existing medium. Smoller and Temple approach the problem by asking a different kind of question. Instead of trying to quantize gravity or dig into the microscopic structure of space-time, they wondered whether Einstein's original equations, interpreted properly and with a bit of help from shockwave theory, could describe the Big Bang in a way that avoids infinite densities and singularities altogether. What if the Big Bang didn't need to be the beginning of everything, but instead the propagation of a sudden change? In fluid dynamics, a shockwave occurs when there's a sudden jump in pressure, temperature, and density. Think of the blast front from an explosion or the boom of a supersonic jet. These are places where conditions in a medium change so fast that the normal rules of smooth flow no longer apply. But even though the changes are abrupt, they are still governed by precise conservation laws of mass, momentum, and energy. Smoller and Temple wondered if something similar could be true for space-time and the early universe. Their model builds on a classical solution to Einstein's equations called the Friedmann-Lemaitre-Robertson-Walker, or FLRW, space-time, which describes a homogeneous and isotropic universe. Most Big Bang models begin with this framework, but Smoller and Temple did something different. They embedded a dynamic, expanding FLRW universe inside a larger surrounding space-time, a Schwarzschild space-time, which is usually associated with the geometry outside a spherical mass. Then they used the mathematical machinery of shockwaves to join these two solutions together across a moving boundary. The result is a picture of the universe where the Big Bang is not a singularity at the beginning of time, but a shockwave moving outward through a static, pre-existing region of space. Inside the shockwave, space is filled with expanding radiation and matter. Outside the shockwave, there is a vacuum, or, depending on the version of the model, a cold, empty geometry. The shock marks the boundary where conditions abruptly change from one state to another. In most cosmological models, there is no before the Big Bang, because space and time are thought to be created together in that moment. In Smoller and Temple's model, time already exists. So does space. The Big Bang is not the birth of time, but a transformation within it. The pre-shock region could, in principle, stretch backward forever, or at least as far as classical physics allows. One of the key insights of the model is that the shockwave itself follows well-defined physical laws. It satisfies the Rankine-Hugonot conditions, which are the classical rules for matching solutions across a discontinuity. These conditions ensure that energy, momentum, and the structure of space-time are all consistent on both sides of the shock. This makes the model internally stable, at least within the realm of classical physics. What makes this approach stand out is that it completely avoids the singularity problem without needing to modify the equations of general relativity. There's no torsion, no extra dimensions, no quantum bounce. The shockwave does all the work. It turns a smooth collapse or expansion into a sharply defined event. It reframes the origin of our visible universe as a boundary condition, not a breakdown. Another notable feature of this model is that it allows for a pre-Big Bang region to exist in a purely classical way. This sidesteps one of the major hurdles in cosmology, the fact that densities and temperatures are so high that quantum gravity is expected to dominate. But since the shockwave model never goes to infinite values, it doesn't need quantum gravity to explain the early moments. It stays within the familiar world of differential equations and metric matching. There are some curious consequences. For example, the pre-Big Bang region outside the shockwave could contain information about the overall geometry or structure of a larger universe. It might even offer a place to test certain kinds of boundary conditions, things that in other models are hidden behind the veil of a singular beginning. There's also the idea that the shock could, under the right circumstances, leave traces in the radiation background of our universe, though detecting them would be extremely difficult. Smoller and Temple's work also intersects with the concept of cosmic censorship. Their shockwave model removes the singularity altogether. Instead of being hidden, it's replaced with a clear, sharp boundary. This might seem to challenge the spirit of the censorship idea, but in practice it avoids the problem entirely. There is no naked singularity to worry about, just a well-defined front where expansion begins. Of course, this model is not without challenges. One of the open questions is how to match the shockwave picture with what we observe today. The universe appears to be nearly flat, filled with dark energy and undergoing accelerated expansion. The shockwave model must reproduce these features, or at least not contradict them, in order to be a serious contender. That means adjusting parameters carefully and making sure the post-shock behavior aligns with observed cosmic evolution. There's also the issue of entropy. In the traditional Big Bang view, the early universe starts in a state of very low entropy, which then increases over time. It's unclear whether a shockwave origin naturally leads to such a low entropy starting point, or whether something else would need to be added to explain the arrow of time. Despite these open questions, the Smoller-Temple shockwave cosmology remains a bold and distinctive proposal. It doesn't try to explain everything at once, and it doesn't venture into speculative quantum territory. Instead, it asks whether the well-established laws of classical physics, when applied in a novel way, can describe the moment we call the Big Bang. It reframes the problem placing emphasis not on what space is made of at the smaller scales, but on how space can change quickly and dramatically within known physics. In a way, this idea recalls earlier stages in science when discontinuities were first introduced to explain sudden changes. The shift from smooth to shock behavior in fluid dynamics revolutionized how people understood explosions, supersonic flows, and star formation. Smoller and Temple extended that thinking to cosmology itself. If stars can form from shock waves, they asked, why not universes? The model invites further exploration. Could such a shock wave be connected to an earlier collapse phase, as in bounce models? Or is it a one-time transformation in an otherwise static environment? What lies beyond the shock? Does it stretch to infinity, or is it part of a larger cycle? These are questions that remain unanswered, but the shockwave cosmology gives a framework in which to ask them, grounded in equations we already understand. Cosmic shock fronts versus quantum fluctuations. Competing origins. Both the shockwave and the quantum fluctuation approaches avoid the traditional Big Bang singularity, but they do so using completely different mechanisms. The shockwave model keeps everything within classical physics and relies on sudden but smooth transitions between known solutions. The quantum fluctuation model suggests a much deeper change, one that rewrites the structure of reality itself. Each one offers a different kind of simplicity. Shockwave cosmology is easier to write down with known equations. Quantum fluctuation theories offer a possible explanation for why the universe appears flat, uniform, and filled with quantum fields. One of the main points of comparison between these ideas lies in the structure of the CMB. In quantum fluctuation models, especially those tied to inflation theory, tiny differences in energy levels at the quantum scale are thought to grow into the large-scale structures we see today. Galaxies, clusters, and even the ripples in the microwave background all come from the stretching of quantum noise during inflation. These models have been tuned to match observations with high precision, especially in terms of the statistical patterns in the background radiation. Shockwave cosmology, on the other hand, starts with a smooth wavefront. It doesn't naturally include inflation, which makes it harder to explain some features, like the nearly scale-invariant distribution of fluctuations across the sky. That doesn't mean it can't do it, it just means the model might need extra ingredients or a reinterpretation of the shock's properties to produce those small variations. The model may need to include slight irregularities in the wavefront or allow for interactions between the shock and pre-existing matter or fields. In the quantum fluctuation picture, time emerges from a more basic state. Before the universe, there was no ticking clock. There was only a set of probabilistic possibilities. Once the fluctuation occurred, time began flowing as we know it. The shockwave model, in contrast, treats time as always existing. The wave moves through time like any other physical object. This has implications for how we think about causality and the origin of cosmic laws. If time existed before the Big Bang, so might the rules that govern physics. If not, then those rules must somehow arise from the fluctuation itself. One of the puzzles of modern cosmology is that the early universe appears to have had very low entropy. Quantum fluctuation models struggle to explain this because fluctuations from a vacuum state should statistically favor high entropy configurations. It's hard to get a big, smooth, low entropy universe from random noise. Some physicists try to resolve this by proposing a multiverse where our universe is just one of many, and we happen to live in the rare one with low entropy. But this explanation is hard to test. In shockwave cosmology, the low entropy might be easier to justify. The model begins with a sharp, classical boundary, and the matter inside the shockwave starts from a specific, tightly defined state. That starting point can be constructed to have low entropy, since it arises from a known geometric transition rather than from random fluctuations. This gives shockwave models a potential edge in explaining why the early universe was so ordered. Testability is another key point. Quantum fluctuation models are often tied to inflation, and inflation has made clear predictions about the spectrum of temperature fluctuations in the microwave background. These have been largely confirmed, although there is still debate about fine details. But the actual fluctuation that starts the universe, often called quantum tunneling from nothing, remains beyond direct observation. It's a philosophical and mathematical idea, not something we can test in a lab. Shockwave cosmology might offer more room for testable predictions, at least in theory. If the shockwave interacts with the surrounding spacetime in a particular way, it might leave imprints, edges or patterns in the CMB, or unusual features in large-scale structure. Some versions of the model predict subtle anisotropies, slight differences in direction that could be measured with future surveys. Others might imply a preferred frame of reference, which could show up in gravitational wave observations. Yet both models share a deep challenge. They must each explain why the universe looks so flat, so uniform, and so fine-tuned. The quantum fluctuation model answers this with inflation, but this inflation itself requires careful tuning of the inflation field and its potential. The shockwave model avoids inflation entirely, relying instead on initial conditions chosen to fit observations. In both cases, the theories can be made to match the data, but they do so by adjusting their starting parameters. That raises the question of whether one is more natural than the other. Another complication is that the two models might not be as distinct as they first appear. Some researchers have suggested that shockwave-like behavior could emerge from quantum processes, or that a classical shock might represent a coarse-grained description of a deeper, fluctuating system. It's also possible that both are partial descriptions of a bigger story, that the universe emerged from a quantum fluctuation, but then transitioned into a shockwave-like phase that expanded into classical spacetime. For now, we lack the tools to decide definitively between these views. Future missions studying the early universe, such as improved microwave background satellites, gravitational wave detectors, or high-resolution galaxy surveys might help. If shockwave cosmology is correct, it may leave sharper boundaries or unusual distributions in space. If the quantum model is right, we may find deeper support for inflationary theory or signs of multiverse-like effects. As different as they are both trying to explain the same cosmic riddle: why there is something rather than nothing, and how the patterns we see in the night sky can be traced all the way back to the beginning. Time reversal symmetry and the white hole hypothesis. In physics, symmetry often tells us something important about the way the universe works. Some of the deepest laws we've discovered are based on the idea that if you change your point of view, or flip time, or reflect space, the rules stay the same. One of the most powerful of these is called CPT symmetry. It says that the laws of physics remain unchanged if you flip three things at once: charge, parity, and time. This is built into the foundations of quantum field theory and is one of the cornerstones of modern physics. If the Big Bang was not the beginning of everything, but instead the result of a kind of bounce or flip, then it might be described in terms of time reversal. CPT symmetry supports this idea. If you take a black hole and flip time, then you should get a white hole. If the laws of physics are symmetric under CPT, then there should be no fundamental reason why a white hole can't exist. But the key here is that you have to flip all three: charge, parity, and time. That makes things more subtle. It doesn't just mean running a film in reverse. It means imagining a world where particles become antiparticles, left becomes right, and time flows backward. This leads to one of the more radical versions of the idea: the possibility that another universe exists on the other side of the Big Bang, running backward in time relative to ours. In this mirror universe, everything would be made of antimatter instead of matter, and processes would unfold in reverse. What we call the past would be their future, and their Big Bang would be our Big Bang, viewed from the other side. Some models actually build this idea into their framework. They start with a combined universe that's symmetric under CPT, and our universe is just one half of that larger structure. The other half is a time-reversed mirror, expanding in the opposite direction through time. In this way, the Big Bang isn't a singular origin. It's a kind of central point, or bounce, between two expanding universes. This is different from the idea of a multiverse, where each universe is separate and possibly disconnected. In the CPT symmetric model, the two universes are deeply connected by the very structure of time and the laws of physics. One is the time reverse of the other, and together they restore the symmetry that physics seems to demand. This view also gives an elegant solution to some long-standing problems. For example, why is the universe so low in entropy at the start? If you have two mirror universes with time flowing in opposite directions, then each one sees its own Big Bang as a low entropy beginning. From the point of view of the full structure, entropy is symmetric. But from inside either universe, it looks like time only flows one way, from order to disorder. There's also the matter-antimatter problem. In our universe, there is much more matter than antimatter, and nobody knows why. But if there's a mirror universe on the other side of the Big Bang filled with antimatter, then the total amount of matter and antimatter in the full CPT symmetric system would be balanced. We just happen to live in the matter half. Some versions of this idea even suggest that this mirror universe could leave traces in ours. There's no direct way to look into the other universe, but if the Big Bang was truly a time-symmetric event, there might be leftover fingerprints. While CPT symmetry works beautifully in particle physics, it's not clear how to apply it to an entire universe. Time reversal on a small scale is easy to describe, but on a cosmic scale, it becomes harder to define. What does it mean for an entire universe to run backward? And how do you reconcile that with what we see? A universe that expands, cools, and forms galaxies over billions of years. Another difficulty is the arrow of time. In a CPT symmetric pair of universes, each side would have its own arrow of time. But if the two sides are connected through the Big Bang, then we have to explain how that connection preserves the flow of cause and effect in both directions. That's not easy, and current models are still working out the details. Even with these open questions, the idea remains a fascinating possibility. The Big Bang becomes a bridge, a white hole, not in space, but in time. And through that bridge might lie another cosmos, just as real as ours, but with time running in reverse. The two universes together would form a kind of mirror image, balancing the books of existence. How the universe looks when viewed as an expanding white hole. Imagine taking the equations that describe a white hole and looking at the space inside it. What would that space feel like if you were living in it? To begin thinking this through, we have to turn to the language of general relativity. The equations that describe the space-time curvature also give us specific solutions for different kinds of space-time. The metric, the mathematical object that tells us how distances and times are measured, is different for a black hole, a white hole, or a simple, flat space. Many of the features of an expanding universe already resemble what you'd expect inside a white hole. For example, all galaxies are moving away from each other, as if flung outward from some central event. When we look deeper into space, we are also looking further into the past. We see a dense, hot origin, something that once held a great deal of energy in a very small space. In relativity, light cones describe the possible paths light can take through space-time. They also show how cause and effect work in a given geometry. In an expanding universe, light cones tilt outward with time. That means that as space expands, the distance light can travel grows larger. Observers who were once out of reach from each other gradually come into causal contact as the universe gets bigger. In a white hole, the same behavior is seen. Light cones tilt outward, because everything is being ejected. Events that happen closer to the origin send light rays outward, and those rays can reach further and further as time goes on. So, if our universe is the inside of a white hole, we would expect the structure of light cones to match what we actually observe, and they seem to. Another observable quantity is the expansion rate of the universe. This is measured through something called the Hubble constant. By looking at how fast galaxies are moving away from us at various distances, we can estimate how quickly the universe is growing. One of the puzzles in modern cosmology is that this value doesn't come out the same depending on how you measure it. Observations of the early universe, like those from the CMB, give one number. Measurements from nearby galaxies give another, slightly higher value. This mismatch, known as the Hubble tension, might have something to do with how we're modeling the universe. Some have suggested that if we were living inside a white hole-like region, the equations we use to describe expansion might need to be adjusted. That adjustment could affect how we interpret light and motion over large distances and possibly help resolve the tension between early and late-time observations. In a white hole, everything flows outward from a central point, and there's a direction to that flow. In our universe, entropy increases with time. If the universe is the inside of a white hole, the outward motion and the growth of entropy would go hand in hand. Every moment would see the universe becoming larger, more disordered, and more dilute, which is exactly what we observe. In a traditional white hole, no matter can enter once it's formed, but our universe is not closed in that way. Matter and energy move freely. Black holes form, stars collapse, radiation travels across billions of light years. Does that behavior fit with the idea of a sealed-off white hole interior? Or do we need to modify the idea, perhaps imagining a more flexible boundary, or a white hole with properties different from the idealized version found in equations? Even with these open questions, the core idea remains testable in principle. If our universe is the inside of a white hole, then there may be subtle differences in how light travels, how matter clumps, or how expansion changes over time. These differences could show up in future observations, especially those looking at gravitational waves, high-energy cosmic rays, or the precise shape of the cosmic background radiation. Gravitational echoes. Do white hole predictions match CMB anomalies? The CMB stretches across the sky in every direction, and for the most part it's incredibly smooth. The temperature varies by only a few parts in 100,000. But hidden within this smoothness are strange details. A few features don't fit the patterns we would expect. These odd spots and alignments have raised questions. To understand what's going on, we first need to take a closer look at the CMB. Discovered in 1965, the CMB has since been studied in detail by several space missions, including COBE, WMAP, and PLANCK. These satellites map the tiny temperature variations across the sky, revealing a faint lumpiness in the early universe. These lumps later grew into galaxies and clusters. The patterns match what you would expect from small quantum fluctuations that were stretched out during cosmic inflation. But not everything lines up perfectly. Some parts of the CMB seem to break the expected rules. For example, there's something called the cold spot, a large patch of the sky that's unusually cool. Then there are the low multipole alignments, which means that some of the largest structures in the CMB map line up in the same direction, something that seems too ordered to be random. These features are subtle, and some scientists think they might just be chance, but others believe they point to something deeper. That's where white hole models come in. If the universe began as the interior of a white hole, then perhaps these features are not so surprising. If our universe is the white hole's inner expanding space, then maybe some of the patterns we see in the CMB are echoes, not of quantum fluctuations alone, but of how that expansion was seeded. In a typical inflationary model, the early universe is driven by the inflaton field. In white hole-based models, the geometry of space from the very beginning is different. The expansion isn't caused by a field, but by the structure of the space-time itself. Some versions imagine a bounce, others picture a singular point of ejection, like a white hole releasing everything outward at once. These setups might imprint certain directional features on the CMB, such as preferred axes or patterns of coldness that are difficult to get from a smooth inflate-on field. One way to explore this is by simulating how light would travel through a white hole interior. Because the geometry bends space-time differently than in a standard model, it might cause small variations in the way photons scatter and spread. When those photons finally reach us, after 13.8 billion years of travel, the imprints they carry might reflect the shape of the original bounce or release. Researchers have tried to compare these white hole-inspired geometries to real CMB data. One approach is to examine the angular power spectrum, the breakdown of CMB temperatures by size scale. Most of the pattern follows predictions well, but at the larger scales there are slight dips and alignments that could hint at a different origin. For example, in a universe born from a white hole, there might be a limit to how connected different regions can be. That could create suppressed power on the largest angular scales, just like what Planck data shows. Another method is to study the cold spot itself. While some scientists have suggested it cold be caused by a large void in space, a region with less matter than average, others have found that explanation lacking. A white hole, by contrast, might naturally produce such a spot due to how energy and matter are distributed during the initial expansion. If matter was ejected unevenly, or if the early geometry had small asymmetries, they could become large-scale features as the universe grew. The main challenge is that white hole models are hard to calculate in detail. Unlike inflationary theories, which have been refined over decades, white hole cosmologies are newer and less developed. The equations that describe them are complex, and it's not always clear how to connect them to data. Plus, some versions rely on physics that's still theoretical, like quantum gravity or unknown forms of space-time structure. Even so, some progress has been made. A few teams have constructed simple white hole models and run simulations of what the CMB would look like in such a universe. The results are mixed. In some cases, the models can reproduce large-scale anomalies better than standard inflation. In others, they introduce new problems. For example, white hole-driven expansion may struggle to produce the precise level of fluctuation needed to match small-scale structure. Or it may require tuning the initial conditions very carefully, something scientists usually try to avoid. Another question is whether gravitational waves could help decide between these models. Inflation predicts a certain background of gravitational waves, which future telescopes may detect. A white hole-born universe might produce a different signature, or perhaps none at all, depending on how the bounce or release happened. That means future observations, especially of the CMB's polarization or of gravitational wave backgrounds, could help confirm or reject some versions of the theory. Some scientists have also explored whether the curvature of space offers clues. Standard cosmology says the universe is flat, and current measurements support that. But some white hole models predict slight curvature, either positive or negative. If more precise measurements show that space is not perfectly flat, it could support those models. Alternatively, the models may need to be adjusted to stay consistent with what we see. Whether or not white hole models are correct, the anomalies in the CMB remind us that our understanding of the universe's birth is still incomplete, and that the sky might still be whispering secrets from the very beginning. Big Bang nucleosynthesis under white hole conditions. Big Bang nucleosynthesis, or BBN, is one of the most precisely tested parts of cosmology. It refers to the formation of the lightest elements, mainly hydrogen, helium and lithium, in the first few minutes after the universe began. The nuclear reactions that occurred during this brief period set the stage for all chemical evolution that followed. Any model claiming to describe the early universe must reproduce the observed abundances of these elements with high accuracy. That includes models where the Big Bang is replaced by something more exotic, like the interior of a white hole. To see whether a white hole-based origin can hold up under this kind of scrutiny, scientists look at how nuclear reactions would behave under altered conditions. In the standard picture, BBN begins when the universe is about 1 second old and cools from about 10 billion Kelvin downward. The key processes involve neutrons and protons combining to form deuterium, then helium-3, helium-4, and trace amounts of lithium-7 and beryllium-7. These reactions are incredibly sensitive to the timing and temperature of the expansion. If space cools too quickly or too slowly, the element ratios can shift in ways that conflict with what astronomers actually see. Now imagine this entire process happening in the expanding interior of a white hole. The first question is how such a space behaves in terms of density and temperature over time. In a normal Big Bang, the scale factor of the universe, how stretched out space is, increases smoothly with well-defined temperature and energy profiles. In a white hole, especially if it involves a bounce or some sort of non-singular geometry, the early expansion may be steeper or more chaotic. Some white hole models suggest a faster initial growth rate, while others propose a brief stagnation followed by rapid acceleration. Each of these expansion histories affects how long the universe spends at the right temperature for nuclear fusion. In some white hole scenarios, the temperature may drop too fast for deuterium to build up before being broken apart by high-energy photons. This would reduce the amount of helium formed. In others, the conditions might persist too long, allowing more fusion than usual and increasing the helium fraction. Either case would leave a clear imprint on the ratios of elements, especially the helium to hydrogen ratio, which we can measure in ancient gas clouds. Observations tell us that about 75% of the normal matter in the universe is hydrogen, and about 25% is helium-4 by mass. There are also tiny amounts of deuterium and lithium. These numbers agree very well with what the standard BBN model predicts. For a white hole model to be taken seriously, it must recreate these numbers within a narrow margin. That's not easy. Any change in the expansion rate or energy density changes the so-called neutron to proton ratio, which is critical in setting the final helium level. Another challenge comes from neutrinos. In standard cosmology, neutrinos decouple from matter just before BBN begins. Their energy density contributes to the total radiation content of the universe and affects how quickly space expands during nucleosynthesis. In some white hole-based models, the number or behavior of neutrinos could differ, either because of different initial conditions or due to exotic processes happening during the bounce or ejection phase. This could again alter the expansion rate, and with it, the nuclear reaction rates. One specific area where white hole cosmology might offer insight or run into trouble is lithium. In the standard model, the predicted amount of lithium-7 is significantly higher than what we observe in old stars. This mismatch, often called the cosmological lithium problem, has remained unsolved for years. Some scientists have wondered whether a non-standard early universe might help fix the problem. For instance, if the white hole environment somehow destroyed or diluted lithium more effectively than a standard Big Bang would, it could explain the shortfall. However, attempts to model such outcomes have not yet shown clear success. In some versions, the altered thermal profile of a white hole-driven universe reduces lithium production only slightly, not enough to explain the full discrepancy. In others, the fast initial expansion causes other problems, like reducing helium too much or producing too little deuterium. So, while the lithium issue remains a potential window into alternative early universe physics, it doesn't yet provide firm support for white hole scenarios. The entropy conditions at birth might also differ in a white hole scenario, and that could influence the initial density of photons relative to baryons, which in turn affects nucleosynthesis. For example, a higher photon to baryon ratio would suppress deuterium formation, while a lower ratio would enhance it. Matching the observed deuterium levels is another strict requirement for any cosmological model, and once again, white hole frameworks must walk a fine line. A final factor is how matter and energy are distributed at the start. In the standard model, conditions are assumed to be homogeneous and isotropic, at least on large scales. But some white hole models suggest a more complicated beginning. If matter was expelled unevenly, or if there were local variations in temperature or density, nucleosynthesis could vary from region to region. This could lead to anisotropies in the light element distribution, something that might show up in the spectra of ancient gas clouds or in the structure of galaxies. At present, there is no strong observational evidence for such variations, but more precise measurements could change that. In the coming years, new telescopes will allow astronomers to study distant, unpolluted regions of space, where the first element ratios are preserved. These measurements may help rule out or support some white hole-inspired ideas, depending on how well they reproduce the fine balance of reactions in those early minutes. Despite these challenges, the idea of testing white hole cosmology through nuclear physics is valuable. Unlike vague geometric features or hard-to-measure gravitational echoes, light element abundances offer hard numbers. They give researchers a way to filter models based on clear physical processes. If a white hole-driven universe can't match these numbers, then it's likely incomplete. On the other hand, if it can reproduce the observed helium, deuterium, and lithium without needing extra adjustments, that would be a strong point in its favour. Big Bang nucleosynthesis remains a powerful tool for judging early universe models. White hole cosmologies must not only match the large-scale structure and thermal background of space, they must also recreate the delicate chain of nuclear events that happened in the universe's first few minutes. The path from protons and neutrons to helium and lithium may seem straightforward, but it leaves little room for error. Any model, no matter how creative or mathematically elegant, will ultimately be judged by whether it can explain what we actually see when we look into the oldest corners of the cosmos. Can we ever observe a white hole or its remnants? High-energy astrophysical events like gamma-ray bursts and fast radio bursts are short but extremely powerful blasts of radiation, and we still don't completely understand all of them. Some happen when stars collapse or when neutron stars crash into each other, but there are other cases where the origin isn't clear. If a white hole were to suddenly erupt, releasing energy all at once and then disappearing, it might leave behind a flash like these. The key is figuring out whether anything in those signals is special. Different enough to suggest they're not just more of the same. Gamma-ray bursts, or GRBs, are among the most energetic things we've ever recorded. Some last just a fraction of a second, others for a few minutes. They come from all directions, implying they're happening across the whole universe. In many cases, we can link them to known sources: supernova, neutron star mergers, or black hole activity. But not all of them match these explanations neatly. Some GRBs are unusually short or don't show the expected afterglow in other wavelengths. These outliers are where some researchers have asked, could this be a sign of a white hole event? To test this, scientists look at the structure of the gamma-ray light curve, the way its intensity changes over time. A white hole explosion would likely be very sharp, with a steep rise and then rapid drop-off, without much lingering activity. Most known GRBs have more complex light curves, often with multiple peaks or long tails. So far, none of the detected bursts show a pattern that's uniquely suited to white holes, but it's hard to be sure. Space is messy. When something explodes billions of light years away, what we detect is only a tiny sliver of what actually happened. Fast radio bursts, or FRBs, are short pulses of radio waves lasting just milliseconds. They're brighter than anything else in the radio sky during that brief moment, and they come from far outside our galaxy. Some FRBs repeat, others don't. The ones that don't repeat are the most mysterious. They come from nowhere, flash once, and vanish. A white hole, if it exploded and never formed again, might look exactly like that. Some theorists have proposed that white hole events could produce FRBs under the right conditions. If the energy emerging from the white hole interacts with surrounding plasma or magnetic fields, it could generate a sharp radio pulse. The problem is that many things can make radio waves. A flare from a magnetar, a highly magnetic neutron star, can look very similar. Still, white hole models offer slightly different predictions. For instance, the pulse might not be accompanied by X-rays or gamma rays, or it might show a strange dispersion pattern, how the pulse spreads out across frequencies as it travels through space. To find out, researchers compare FRB profiles with detailed models. They look at things like polarization, frequency drift, and repeat behavior. If any FRBs show patterns that don't match magnetars or other known sources, but do match what a white hole would do, then that would be a big clue. So far, there are no confirmed FRBs that clearly point to a white hole. But the database of detected events is growing fast. Each year brings dozens of new signals, and some of them are still waiting to be classified. Another place to search is in unusual X-ray sources. Some regions of space seem to emit X-rays without an obvious reason. These aren't bursts, they're more like steady glow or sudden flares with odd features. If a small white hole was surrounded by leftover debris, it might interact with that matter and produce radiation. This idea is speculative, but not ruled out. In theory, such a source could resemble an accreting black hole, but without any infall. Instead of matter spiraling in, radiation would be moving out. Astronomers use space telescopes like Chandra and XMM Newton to study X-ray emissions from stars, galaxies, and clusters. They look for variability, unusual spectra, or strange location. Some X-ray sources, especially those found in dark or isolated regions with no obvious nearby star or galaxy, raise questions. Could one of these be the signature of a tiny white hole remnant? At present, there's no strong evidence, but many faint X-ray sources haven't been fully studied, and more precise instruments in the future might help. When two massive objects collide or suddenly change shape, they produce ripples in space-time or gravitational waves that we can detect on Earth. The LIGO and Virgo observatories have already picked up signals from black hole and neutron star mergers. If a white hole were to explode or form suddenly, it might also produce a gravitational wave signal. The shape of that signal could be very different. It might be brief and symmetric in a way that standard black hole mergers are not. So far, we haven't detected any gravitational wave signals that look like this. But as new observatories like LISA come online in space, the chances increase. A confirmed gravitational wave from a white hole would be hard to ignore. Unlike radio or X-ray signals, gravitational waves pass through space without being absorbed or scattered. That makes them ideal for studying exotic processes in distant parts of the universe. Even if we can't see a white hole directly, we might detect its effects on surrounding matter. If a white hole ejected a large amount of mass and energy in a short time, it might leave behind a kind of scar in the cosmic environment. This could take the form of a strange void or a moving cloud of particles with no clear origin. Radio telescopes, infrared surveys, and high-resolution sky maps might all play a role in identifying these patterns. We can also turn the question around. If white holes existed in the early universe, could they have influenced structure formation? Some researchers suggest that if mini white holes formed alongside black holes, their explosive energy might have seeded density variations, tiny bumps in matter distribution that later grew into galaxies. One reason white holes are so hard to find is that they don't last long. Most models predict that if they exist at all, they would explode and vanish almost immediately. That makes timing critical. Unless we're looking at the right patch of sky at the right moment, we'll miss it. That's why many astronomers rely on automated sky surveys, robotic systems that scan the whole sky regularly and flag anything unusual. The hope is that somewhere, someday, one of those flagged events will turn out to be more than just a flare or a lensing artifact. Some experiments are now designed specifically to catch short-lived phenomena. Instruments like the CHIME radio telescope and the Zwicky Transient Facility are focused on finding transients, things that appear, change quickly, and disappear. These are exactly the kinds of tools that might one day catch a white hole in the act. The search for white holes is a bit like the early days of black hole theory. People knew they existed in the math long before they found ways to look for them in the sky. It took decades of improved technology, better models, and patient observation. The same may be true here. White holes could be hiding in data we've already collected, waiting for someone to ask the right question or notice the right pattern. White hole signatures in primordial gravitational waves. If the Big Bang was a white hole explosion, then the source of the primordial gravitational waves would be entirely different. Instead of being caused by vacuum fluctuations in a smooth, inflating background, the gravitational waves would be produced by a violent outburst of matter and energy from a collapsing or quantum transitioning region. The process would be asymmetric, turbulent, and filled with nonlinear interactions. The waves it generates could have distinct spikes or features, unlike the broad hum expected from inflation. One of the ways white hole-based origins might differ is in the sharpness of the gravitational wave signal. Inflationary waves are often described as red-tilted, meaning that they are strongest at low frequencies and weaken at higher ones. A white hole event might do the opposite, releasing bursts of energy that generate more high-frequency waves. These would not be spread out smoothly across the spectrum, but might show up as bumps or localized peaks. Inflation is supposed to make the universe look the same in all directions. But if the Big Bang was more like an explosion from a specific region, like a white hole mouth, it might have produced waves that carry a directional bias. In other words, the pattern of primordial gravitational waves might not be the same everywhere in the sky. That's something future detectors could potentially test by measuring not just how strong the waves are, but which directions they seem to be coming from. Today's gravitational wave detectors are built to catch waves from events like black hole mergers. These signals happen at relatively high frequencies, from a few tens to a few thousand hertz. But primordial gravitational waves are much softer, with frequencies many orders of magnitude lower. To detect those, we need a completely different kind of observatory. Scheduled for launch in the 2030s, LISA will be a space-based gravitational wave detector, with arms millions of kilometers long. It will be sensitive to much lower frequencies than LIGO, down in the millihertz range. That's exactly the range where some models predict a white hole origin might leave an imprint. If there's a spike in the gravitational wave spectrum at these low frequencies, or a sudden drop, LISA could catch it. There are also even more ambitious missions being proposed, such as the Big Bang Observer or DeCigo. These would go even deeper, aiming to detect the quietest possible gravitational signals from the earliest times. If the universe did start as a white hole, and if that process had even a small degree of asymmetry or turbulence, these missions might be able to pick up the result. One possible feature to look for is a cutoff frequency, a place where the spectrum of gravitational waves drops sharply. In some white hole models, the explosion is a one-time event, with a very short time scale. That would limit the maximum wavelength of any waves produced, creating a ceiling in the frequency range. Inflation, on the other hand, produces waves over a broader range. Detecting a cutoff might suggest a more abrupt origin, like a white hole release, rather than a slow stretch out of inflation. If the white hole event included a specific phase transition or resonance, a moment when energy was transferred suddenly between fields, it might have generated gravitational waves at a precise frequency. This would show up as a narrow peak in the spectrum. Such features wouldn't fit easily into inflation models, but could arise naturally from a burst-like process. In addition to space-based detectors, other methods could be used. One involves pulsar timing arrays. These track the arrival times of signals from pulsars, spinning neutron stars that emit regular radio pulses. A passing gravitational wave can slightly change the timing of those pulses. If enough pulsars are observed over a long period, we can build a map of low-frequency gravitational waves in the universe. These arrays are just now reaching the sensitivity needed to test theories about early universe gravitational noise. Tiny distortions in the polarization of the CMB, especially something called B-mode polarization, could be caused by primordial gravitational waves. These effects are subtle and hard to measure, but they're one of the most direct ways to test early universe models. If a white hole origin predicts a different pattern of B-modes than inflation, and if we measure those differences, we might be able to tell which scenario actually occurred. Researchers are beginning to build simulations of how white hole explosions might behave, how matter and energy move during the event, how space-time bends, and how waves are produced. These simulations take time and require high-powered computers, but they are essential if we want to know what kinds of signals to look for. It may be years, even decades, before we gather enough data to make a firm call. But every step in gravitational wave astronomy brings us closer. What particle physics would look like if the universe emerged from a white hole? If the universe began as a white hole, then the entire stage for particle physics, its timing, energy scale, and structure, would have looked different from the start. And those differences could have shaped how particles formed, how matter came to dominate over antimatter, how the fundamental forces behaved in the earliest moments, and whether dark matter came into being at all. To understand the full reach of this idea, it's important to ask what white hole conditions would mean for the mechanics of high-energy physics at the earliest times. In the traditional picture, the early universe was a hot, expanding plasma, where temperatures were high enough for particles and antiparticles to form and annihilate continuously. Eventually, as the universe expanded and cooled, certain transitions happened. Quarks bound into protons and neutrons. Nuclei formed. Electrons attached to them to create atoms. But even earlier, at energy levels far above anything we can reach in labs, particle interactions were far more exotic. These high energies allowed processes that shaped the large-scale properties of the cosmos. How much matter versus antimatter exists, whether dark matter formed, and how symmetries between forces may have broken. If a white hole seeded the universe, those early conditions change. Instead of a gradually unfolding space with well-understood thermodynamic limits, the beginning could have been marked by a highly non-equilibrium release of energy and matter. Matter might not have emerged from a true thermal equilibrium. Instead, it could have been ejected in a burst, possibly involving turbulence, asymmetry, or quantum gravity effects. That changes the assumptions behind some key particle processes, especially baryogenesis. This is the process scientists believe caused the universe to be made mostly of matter rather than equal parts of matter and antimatter. In most theories, baryogenesis relies on three necessary ingredients: violation of baryon number, meaning matter and antimatter are treated differently; violation of charge parity, or CP symmetry; and conditions out of thermal equilibrium. The last part is crucial. If everything had always been in perfect thermal balance, matter and antimatter would have formed and annihilated in equal amounts, leaving the universe filled with radiation and no atoms. The matter ejected from a white hole doesn't have to be balanced, smooth, or even statistically fair. It could have a built-in asymmetry, favouring matter over antimatter. The shock of emergence itself might serve as the engine that creates this imbalance. If the energy and timing of this release breaks CP symmetry in specific ways, the universe could be born with the right conditions to favour baryogenesis without needing exotic scalar fields. What fields or particles existed at the moment of ejection? In standard cosmology, we trace particles back to a nearly uniform high-temperature state, where quantum fields settle into different configurations as the universe cools. The Higgs field, for example, takes on a non-zero value that gives particles their mass. But a white hole origin could involve a very different starting configuration. The Higgs field might not emerge smoothly. Instead, it could be kicked into its vacuum state by violent transitions during the explosion. This would mean particle masses might not appear in the same staged way we currently model. Another key moment in early particle physics is the electroweak phase transition, when the electromagnetic and weak nuclear forces separate into distinct interactions. Whether this transition is smooth or abrupt matters. A strong first-order phase transition, more like water boiling than freezing, could help generate gravitational waves and affect how particles scatter and decay. In some white hole models, the energy densities and pressure conditions might make such abrupt transitions more likely. That could even open up windows for testing the origin of the universe in particle colliders or by observing relic gravitational wave backgrounds. Then there is dark matter. In many standard models, dark matter is assumed to have formed in the early universe as particles that weakly interact with ordinary matter. The most common idea is that they were created thermally, meaning they were in equilibrium with the hot plasma, then froze out as the universe cooled. But if the beginning came from a white hole and conditions were out of equilibrium from the start, the dark matter production process could be radically different. One idea is that dark matter might have formed non-thermally, meaning not as a result of equilibrium reactions, but as a direct product of the white hole explosion. In this case, dark matter would be a remnant of the ejection process, not something that settled into place as things cooled. That would affect both its expected density and how we might try to detect it. For instance, instead of looking for interactions with normal matter at low energy, we might instead need to look for rare, high-energy processes or specific decay paths that only appear under asymmetric initial conditions. If quantum gravity plays a role in shaping the explosion, it might generate entirely new fields that don't interact with our usual particles except through gravity. These might resemble axions or sterile neutrinos, both of which are candidates for dark matter. The benefit of a white hole origin is that it naturally permits a wide range of energy scales and timing. The transition could happen with more variation than in standard inflationary models, giving these particles a broader window to form. Supersymmetry, another idea in high-energy physics, could also be affected. Supersymmetric particles are partners to the known particles, predicted by certain extensions of the standard model. In many versions of the theory, the lightest supersymmetric particle is stable and could serve as dark matter, but the production of these particles depends on having enough energy and the right field conditions. A white hole universe might produce some of them in different ratios, or suppress their creation entirely if the temperature or vacuum landscape differs from standard expectations. Even the basic structure of space might affect particle behaviour. If the white hole event deforms space-time enough, it might create conditions that alter how fields evolve. Particles might not obey the usual dispersion relations. Quantum fluctuations could be amplified or suppressed. Some theories suggest that Lorentz invariance might temporarily break down near the white hole boundary. That would lead to small, testable violations in how particles behave at extreme energies. Colliders like the Large Hadron Collider may not reach the energy scales of the Big Bang or a white hole eruption, but they can test symmetry breaking, look for CP violation, and search for unusual decays. Meanwhile, detectors designed to look for dark matter could catch signs of non-thermal production if particles appear with unexpected distributions or interaction patterns. Future high-energy experiments like proposed 100 tera-electron-volt colliders or precision neutrino observatories could give further clues. For example, if neutrino masses turn out to be tied to a specific asymmetry generated during the early universe, and that asymmetry doesn't match inflationary predictions, it might hint at a different kind of beginning. A white hole origin changes the nature of the stage on which particles formed and evolved. The models are still developing, and none yet offer a full alternative to standard cosmology. But they show that even in the most fundamental realm, where quarks, leptons, and forces emerge, a white hole origin might rewrite the rules. The challenge of embedding white holes into a quantum gravity framework. The two leading candidates for quantum gravity are string theory and loop quantum gravity. They are very different in their approach, their mathematical tools, and their views on space and time. But both aim to resolve the same fundamental problem: how to describe gravity as something that has quantum properties, just like particles and fields do in the rest of physics. In string theory, black holes, especially when they become extremely small and dense, create real challenges. But string theorists have worked hard to explain the entropy and quantum behavior of black holes by describing them in terms of brains. White holes, however, are harder to accommodate. In string theory, they don't emerge naturally in the same way that black holes do. While time reversal can still be applied, the dynamics of string interactions and the way energy behaves under extreme curvature make it difficult to find a clean white hole counterpart. The singularity at the center of a white hole would need to be replaced with something smooth or well-behaved under the rules of the theory. But string theory doesn't yet provide a mechanism for this. While the idea of a bounce from one universe to another is sometimes considered in speculative versions of the theory, these are usually tied to very specific conditions in a higher dimensional setup and do not offer a clear description of a real white hole as an isolated object. Loop quantum gravity, by contrast, predicts that the singularity at the center of a black hole might not exist in the way we think. Instead, quantum effects could cause a bounce, which opens the door to white holes. In this model, white holes are the future evolution of black holes after an incredibly long time, far longer than the age of the universe. These ideas are still under development and are far from complete. For one thing, the math behind the black to white transition is complex and not fully understood. It involves approximations and simplifications that may not hold in all cases. But it does suggest that white holes could, at least in principle, be made consistent with quantum gravity. A big challenge in both string theory and loop quantum gravity is causality. In quantum gravity, where you need to calculate probabilities across different possible histories, that lack of a well-defined past becomes a serious problem. In string theory, calculations rely on paths or surfaces in space-time. If there's no past to integrate over, those calculations break down. In loop quantum gravity, the same problem arises. How do you connect a network of quantum geometry that has no origin point in time? String theory also faces complications when trying to embed white holes into its landscape. Many string theory models require extra dimensions, and the behavior of objects like black holes or possible white holes in those extra dimensions can differ greatly from what we experience in four-dimensional space-time. Sometimes a black hole in 4 dimensions looks like a string or a membrane in higher dimensions. White holes, if they exist in that framework, may also need to be understood as higher dimensional phenomena, not simply the time reversal of a familiar black hole. There have been attempts to use the so-called holographic principle, a key insight from string theory, to study black holes and time reversal. According to this idea, all the information inside a region of space can be described by data on its boundary, much like a hologram. If this principle holds, then in theory, one could describe a white hole's behavior in terms of data encoded on its boundary. But most work in holography focuses on black holes with well-defined horizons, not on objects that violate time symmetry or lack a causal past. In quantum gravity, the shape of space-time is not fixed. It fluctuates and evolves. But white holes, as currently imagined, assume a specific, highly organized direction of time. That structure may not survive the randomness and fuzziness of quantum space-time. It's possible that in a full theory of quantum gravity, the concept of a white hole becomes meaningless, replaced by a more general structure that doesn't match our classical ideas. Loop quantum cosmology. Loop quantum cosmology is a simplified version of loop quantum gravity, built specifically to deal with questions about the early universe. While the full loop quantum gravity theory attempts to quantize all of space and time, loop quantum cosmology strips things down to their core. It assumes the universe is homogeneous and isotropic and then applies quantum principles to that simplified model. In doing this, physicists can test whether the same ideas that might smooth out the inside of a black hole can also smooth out the singularity of the Big Bang. Loop quantum cosmology does not lead to a true singularity. In loop quantum cosmology, the quantum nature of space causes gravity to behave differently at very high densities. Instead of allowing space to collapse into a singularity, the theory causes a repulsive force to appear at extremely small scales. That force effectively halts the collapse, and the result is a universe that contracts, reaches a minimum size, and then begins expanding again. The idea is that just as matter might emerge from a white hole, the universe itself may have emerged from a previous contracting phase. The key difference is that this process is not just a mirror image of collapse. It includes genuine quantum corrections to the geometry of space and time. These corrections come from the underlying equations of loop quantum gravity, which are based on quantized loops of space rather than smooth curves. At the heart of the model is a new version of the Friedmann equations. In classical cosmology, the Friedmann equations describe how the universe expands or contracts based on its energy content. They are derived from general relativity and work well until you reach extreme conditions, like those near the Big Bang. Loop quantum cosmology modifies these equations. The standard energy density term is replaced with a quantum-corrected version that includes a maximum allowed energy density, sometimes called the critical density. When the universe reaches this density, the quantum corrections become dominant, and instead of continuing to collapse, the universe bounces. Mathematically, the modification comes from replacing the classical geometry with a quantized geometry. In classical cosmology, space-time is treated as a smooth manifold, but in loop quantum cosmology, space-time is built from discrete units, each associated with a loop or spin network. These loops introduce a minimum length scale, the Planck length, below which space cannot be divided. As the universe contracts, these units of geometry become important. The equations show that the energy density cannot grow beyond a certain limit because of how the loops interact. The model has been worked out in detail using both analytical solutions and numerical simulations. The results show that for a wide range of initial conditions, the universe always undergoes a bounce when it reaches the critical density. The equations also allow researchers to study the transition from the contracting phase to the expanding phase and to predict how quantum fluctuations behave during this time. These fluctuations may leave imprints in the structure of the universe. The bounce in loop quantum cosmology could solve several long-standing problems in cosmology. It might offer an alternative mechanism for inflation. It could also potentially preserve information through the bounce. In a classical singularity, all information about the prior state is lost. But in loop quantum cosmology, the quantum equations allow for continuity. The wave function of the universe evolves through the bounce, suggesting that the pre-bounce universe could have influenced our current state. If true, this would have deep implications for the nature of time, memory, and causality. If the universe underwent a bounce, then what determined the conditions of the prior contracting phase? Were they random? Were they set by some deeper law? Loop quantum cosmology does not yet answer this question fully. Some versions of the theory suggest that the contracting universe may have been much like ours, but running in reverse. Others propose that the pre-bounce universe was governed by entirely different rules, possibly containing different particles or physical constants. Efforts are also being made to connect loop quantum cosmology to more general versions of loop quantum gravity. So far, the bounce model works well in highly simplified settings, where the universe is assumed to be the same everywhere. But real space is not perfectly uniform, including inhomogeneities, variations in density and structure, adds complexity. Researchers are developing more advanced models that include these features, hoping to understand how the bounce behaves under more realistic conditions. One path involves applying perturbation theory to the bounce. By introducing small fluctuations into the model, physicists can see how those fluctuations evolve before, during, and after the bounce. Early results suggest that many features of the bounce survive these complications and that the fluctuations remain well behaved, but the calculations are tough and the full picture is still emerging. There are also ongoing debates about the role of time. In loop quantum cosmology, time is often defined using internal variables, such as the volume of space. This makes it possible to describe the bounce in terms of a before and after, even if there is no absolute time. Still, the meaning of time through the bounce remains a puzzle. Implications for cosmic topology: closed versus open in a white hole universe. The shape of the universe is one of the most basic questions in cosmology, but also one of the hardest to answer. This is the study of cosmic topology, and if the Big Bang were the result of a white hole, that changes how we think about the problem. If the universe began as a white hole, there would be a special kind of boundary condition at the beginning. A white hole is not like a normal explosion that starts from an empty point. It has a surface, a horizon, and everything that exists inside it must have come out through that horizon. This sets up a particular kind of causal structure. In some models, that initial surface might be smooth and connected like a hypersphere or three-sphere. In others, it might already be twisted, looped, or cut in ways that shape the entire universe that follows. A three-sphere is like the surface of a regular sphere, except with one more dimension. If you travel in a straight line in such a space, you eventually return to where you started. There's no boundary, no edge, and no infinite stretch. In a white hole origin scenario, a three-sphere is a natural candidate. It gives the white hole something to expel, a closed, compact ball of space that unfolds into a full universe. But other topologies are possible too. A Hadron torus egi siktea, a periodicus heterokal. Think of a cube where each face is connected to the opposite face. This kind of space is finite in volume, but has no edges. It can also produce repeated patterns in the sky, because light from a distant object could wrap around the universe and reach us from more than one direction. If the Big Bang white hole existed in a parent space with a toroidal topology, then its explosion might preserve or reflect that topology. There's also the possibility of open topologies, spaces that extend forever but still have interesting shapes. A negatively curved universe, like a hyperbolic manifold, can be infinite, but still have structure. These types of spaces can contain pockets or repeating motifs if they are compactified, cut and glued in clever ways. Again, The topology could be inherited from the white hole's internal geometry, depending on how its horizon and boundary conditions are defined. Cosmic topology leaves traces even if the universe is very large. If the universe has a non-trivial topology, if space loops around or has a closed shape, then light from the same early event could reach us more than once. This would show up as matching patterns or circles in the CMB sky. Scientists have searched for these signs. Some looked for so-called circles in the sky, where the temperature fluctuations in two distant parts of the sky would be nearly identical because they came from the same region of space seen along different paths. Others examined statistical features, whether certain wavelengths were missing or suppressed in the CMB power spectrum, which could suggest the universe isn't large enough to support them. So far, most of the data is consistent with a flat, infinite universe, but that doesn't rule out complex topologies. It just means that if the universe does repeat or loop, it does so on scales larger than our observable patch. That could mean that the horizon from which everything emerged was much larger than what we can now observe, or that the topology of space changed rapidly after the bounce. Perhaps a white hole might constrain the universe to be spatially closed. Since the white hole horizon acts as a kind of boundary to the past and nothing can enter it, the space it generates might be required to be compact. This would make sense from an energy balance point of view. A closed universe has no edge, no infinite reservoir of space, and no way to leak information or energy outward. Everything is contained, and everything has to come from inside. The Einstein field equations are very sensitive to initial and boundary conditions, and small changes can lead to big differences. During a bounce, when classical space-time breaks down and quantum gravity takes over, the topology of space might be in flux. Some models allow for topology change, while others forbid it. Loop quantum gravity tends to preserve topology, while other quantum cosmology approaches remain agnostic. Whether the universe is a bubble, a loop, or a complex stitched-together shape, its topology shapes how light moves, how matter clumps, and even what paths are possible through space. If a white hole lies at the beginning of it all, then the way that white hole formed, its shape, its boundary, its quantum structure, could be the key to understanding the grand shape of everything we see. After hearing all these mind-bending ideas, where does your opinion lie? What do you think about the likelihood of the Big Bang being caused by a white hole? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.